Okay. Let me check everything's fine. The stream, let me check. Okay, I think we should be okay. Hang on, I need there we go. Okay. So this is now going to be A-level maths revision for paper 2. So obviously paper 1 was today's Friday, so it was Wednesday. No, today is Thursday. Thursday. So yesterday. And what I've done now is obviously I've seen the paper, I've seen the questions, and what the aim is now and today is to look at the questions that haven't come up, the topics that haven't come up, the questions, the sort of questions that come up that didn't come up, so for paper 2. And actually, where was it? And so the topics I predict will come up, although I don't think is anything special. But because of what came up in paper 1, I think this will be in paper 2. So binomial expansion, some sort of like differentiation. There'll be lots of differentiation, I reckon. And I think quotient rule, implicit differentiation, parametric differentiation. And like maybe a tricky differentiation one as well. I'm not sure. And then there's some parametric work again with differentiation or just normal stuff like finding combining an equation to get y in terms of x and stuff like that. Proof by contradiction, partial fractions, differential equations. I don't think there'll be a lot of integration in the next paper, but I think integration will come up with differential equations, and maybe integration with partial fractions. Combine the two together. There'll be some function work, so stuff like finding inverse, composition, the range and domain, all that sort of stuff. Modulus, so have to sketch a modulus or solve a modulus equation, stuff like that. Some more sequences and series. Obviously, there was arithmetic, but there wasn't a lot to it. So I'd expect geometric and recurrence stuff to come up as well. Trapezium rule, potentially logarithms. So using the log rules, equations, making and solving equations with logs, and logarithmic model questions. And then some trig modelling, harmonic stuff as well, potentially. And then quadratic modelling and potentially straight line modelling. But I think that kind of came up in paper 1. But those are the, what was it, 13 topics I reckon will come up. So you could there or about make a paper out of it. Okay, so that's what I've done. So based on those topics, I've essentially looked at the past papers and got the questions from there, and that's what we're going to do today. Look at some questions here. If I probably won't have time to do all of it. It's 103 marks worth of questions. It'll be next time. So uh, I think I should stream today. Well, today and then. When's the next day? Monday and then Wednesday. Obviously, Wednesday will be the night before. So there should be 3 sessions. I think this is going to be the first one. So if I don't do all of this now, it'll be in the Monday session. And yeah, that's really the plan. Also, it probably isn't a bad idea, especially to look at paper 2 in June 2022. And actually, October 2020, paper 1, because these 2 papers they have a lot of the topics that haven't come up in paper 1, that have come up in paper 1. So they have a lot of the other questions, right? These two would be really good to practice. But really, again, ideally, you should practice everything. You should practice as many past papers as you can. But yeah, particularly during 2022, because actually, I did it. I looked at the yesterday's paper side by side with paper one from June 2022, and they're basically identical. I think the examiners got very, very lazy. So that's not a bad idea. But don't expect paper June 22. Don't expect paper two from June 2022 to be like this. Okay, the examiners will probably know people will cotton on to the similarity. They won't make it that predictable. Well, I hope not. But these two papers were really good practice. And I've went over 2022 paper two as well recently. If you check my past paper playlist, but yeah, um, and I've also picked some questions from here there as well, which we're going over today. Obviously, this one, the first one, is from that paper. But yeah, that's really it essentially. I guess we'll get started. Okay, so question one. Oh, here we are. Question one. Is a sort of generic recurrence relation question. So recurrence relation looks like this, right? So we have terms defined by the previous term. So here, this will do the previous term, and then we use it to get the next, and then that would be that you substitute back in to get the next term after that, and so on and so on. And we have to have a starting number as well for that to work. That's all it is really. Okay, so we have the sequence. We need to show that it's periodic and to state the order. Okay, so periodic makes like with a sine graph, periodic means it repeats itself. But to find that out, really, and with any sequence of series that is a bit unfamiliar, just work out the first few terms, right? So we already have A1 is 3. Then the next term, A2, well, if we use it, it's going to be 8 minus A1, which is going to be 8 minus 3, and that'll be 5. Then let's have a look at A3. So then that'll be 8 minus A2, which should be 8 minus 5, and that will get you 3. And then just we can check the next one maybe. A4 will be 8 minus A3, which should be 8 minus 3, which should be 5, and hopefully you spot there's a pattern, right? It's alternating between 3 and 5. So that means it's periodic because it's returning back to the same numbers. So therefore, sequence is periodic as it alternates between the same numbers, right? The same terms, the same numbers, right? Which are 3 and 5. Okay, that sort of thing. To justify it. And that's what it means, right? Periodic. Like with sine wave, the period and the cos wave is 2 pi, right? Every 2 pi, it repeats its same shape, okay? The same sort of idea here. It's periodic because it repeats the same numbers, the same terms. So it's periodic in that sense. Okay, and then II, the order. Well, the order is basically just saying how many terms there are in the sequence. So kind of like how the sine wave is periodic. The period would be 2 pi, right? That's telling you the amount you between the starting point and then when it next repeats itself. That's essentially the same idea here. So as our first term is 3, how many terms until it repeats itself? Well, we have 3, then we have 5, and then we have 3. So actually it's 2 terms. So the order would be 2. Okay. So essentially in a periodic sequence, the order is how many numbers there are, right? Because then after you have that amount of numbers, 3 and 5, then it repeats back to itself. So the order there would be 2. Okay. Cool. Then part B is we need to find the value of this little summation here, 85 an, between n is 1. Okay. And you need to recognize what this sort of summation. This it's called sigma notation, and what that's saying is really from if you substitute n is 1 and n is 2, n is 3 to 85. you're summing A1, add A2, add A3, add A4, and so on till the last term A85. Okay, so hopefully you realise that. So we're just replacing n for 1, 2, 3, 4 to 85, and we're adding them because this little shape here means sum. So it's the series, so you're adding the terms. Okay. So again, like I said before, the best thing then with an unfamiliar sort of series is just add the first few terms, right? Let's see what happens. So remember, A1 was 3, then we got 5, then we have 3, then we have 5, and then it goes on, and then we have the last term, A85. Okay, I'm maybe not too sure what it is yet, but that's fine. Let's leave it there. Hopefully you recognise we have a patterns of 3 and 5s. And so essentially we're going to be adding some lots of 3 and some lots of 5. Okay, how... Obviously you might recognise this, but how are we going to split the series, or how are we going to work it out? Well, you could maybe think we do 2 of each, right? Because it's 2 numbers, so we say 2 lots of 33 and 2 lots of 5. Well, not 2 lots, sorry. There'd be there'd be equal amounts of 3 and 5, right? Because it's only 2 terms. But the problem is, if we divide 85 by 2, which is how many terms there are, you get a decimal. So it's a bit awkward. So it's a bit hard to see how to split it. However, what we can instead say is, what if we consider this to then make an even number? What if we add the first 84 terms and then add the last term by itself? Hopefully you can see that, because this is saying between 1 and 84. And then we have the last term A85, and that's exact same as this. And now this makes our life a lot easier because 84 is an even number. So what that is saying is now we can now split the 3 and 5s, because there's 2 of these numbers, into 2. So we can exactly say, well, what's 84 divided by 2? If we're going to split this up in 2s, what's the half of 84? Well, it's going to be 42, right? So then what we can say is, well, it'd be 42 lots of 3s and 42 lots of 5s, and then we have this A85 left over. Okay, so then really the last sort of mission is to find A85. So for that, you just got to recognize the sort of pattern that's going on with the series, right? Well, I'm going to list it again. So A1 is 3, A2 is 5, A3 is 3, A4 is 5, and so on. What do you notice between the n, the 1, the 2, and the 3, and what the number is? And hopefully you realise if n is odd, we get 3, and n is even, we get 5. So actually, 85 is odd, so that's going to be 3, right? If you think about the pattern. So then you just put that into the calculator, and then we get our result. 42 lots of 3 add 42 lots of 5 add 3 is 339, and that should be your result. Okay, and in general, this is a really good trick with series and recurrence relations to help you really visualize and see how to split the sum up when you have an awkward number like 85 here. So I guess as another example, say if we had the series 3, 5, 11. I think it's the same one last time, but 3, 5, 11 then goes back to 3, 5, and 11, and so on. And say if we had to add the 99, well, no, that's weird. The 100 series, right? The first 100 terms of AN, where A1 was 3, 5, and 11, and 3, 5, 11. Well, you can't exactly say it's well, it's like the 33 lots of 3, 33 lots of 5, 33 lots of 11, and stuff like that, because there's 100 terms. That's not divisible by 3. So really, what you could do is with this sort of thing. Well, how can we get this number down to make it a multiple of 3? Which means we can evenly divide all these 3 terms by 3. And I think 99, right? Because 99's divisible by 3. And then I can add the last term, which is A100 here. Well, 99 is divided by 3 is 33. So that means when I do that, it's going to be 33 lots of 3, add 5, add 11. And then we have this last term here. Well, I noticed, well, A99 was the term before it. That's a multiple 3. If I also notice the third number, the third term and the sixth term is 11. So therefore, the 99th term, which is also multiple 3, I can clearly see in multiple 3s, right, is going to be 11. So that means this also is going to be 11, right? If you think about the pattern. So that means the next term is going to be 3, because obviously 11 then goes to 3. So that would be 3, and then you put that into a calculator, you get this series here. If you add all the first 100 terms in this series. So that sort of idea of splitting up. When you, again, if you have an awkward number that doesn't quite split all the numbers you have up nicely, go back a few terms to then get a number that is nice, like 99, which can divide by the 3 numbers, and then you just add on the last term or so, and then hopefully you can work out what this term is. It's a lot easier than trying to really like faff about. I don't know. I find that that's one approach anyway. Obviously, if you have your own, that's cool. But that's one way you can approach this sort of series without much mess. But yeah, okay, that's that question. Cool. Question 2. Again, this is on page June 2022, paper 2. So we have these values for x and y, and we need to use the trapezium rule to estimate this integral here. So this formula, in the formula book, you are given the trapezium rule. I've copied and pasted it here exactly, and that's going to be crucial, right? So really, you got to recognize how to use it, right? But you are given it, and really, if you know how to interpret it, and I'll go over how to use it now. But if you know how to use it, it's actually pretty simple. So before you use the formula, you're going to need to work out this h. And this h is given here. So if we have the integral, part A, the integral between 9 and 3 of log 3 to the 2x. Well, first of all, your b minus a, those are your upper and the lower limits. So that means your h is going to be between 9 and 3, which should be 9 minus 3. And then you have your n, so that'd be 6 over n. Now, the n's probably the trickiest bit, but this is where you use the formula to guide you. So the n is referring to the number of strips, so the number of trapeziums in the trapezium rule. So if our graphs say look like this, if we have 1, 2, 3, 4, 5 points, it's going to be like first point, second point, third point, fourth point, and the fifth point. So actually, how many trapeziums we've got? 1, 2, 3, 4. So actually, n, the number of trapeziums or strips, is going to be 4. But how would you kind of get that without, kind of considering the geometry, right? And that's where this formula comes in. So notice what this is doing here. So these are adding all the y values of our points, which are here. But notice it starts at y0, and then it goes to y1, y2, and then yn minus 1, and then yn at the end. So that would mean that has to be y0, and then that would be y1, y2, y3, and then y4. So actually, by counting like that, you can then deduce n, the final bit, has to be 4, which is what we got here. So again, use the formula to guide you if you're not unsure about what the n is. I think the n, deciding what the n is, probably the trickiest bit, I feel like. But once you got that, well, we found our h value. So 6 over 4, again, is what, 3 over 2. Seeing this after being out of uni over a year now, suddenly flashbacks to simpler time. Oh, I know, I know. I've been the same. I've been out of uni for, when was it now? About 5 years and that. No, 5 years, sorry, 3 years. I haven't done any maths since until like a few weeks ago, really. But I thought I'd managed to do some A level stuff to help people out for the exams. But I'm getting to grips with it a little bit as well. But I, I don't know. I kind of get most of it though still. But yeah. Anyway, so we have a H now, so we've got all our ingredients right to find this area here by the trapezium rule. So if you just apply the formula, that's going to say the integral is going to be a half of H, half of 3/2, times by this whole bracket here of y0. Right, again, y0 is our first y value, so it's going to be 1.63. And then the final y value, which is 2.63. And then we have to add two lots of y1, y2, and then and then the term before it. So the other values, right? So two lots of 2, add 2.6, and then 2.46. And then that's really just a job for the calculator, right? So put that into the calculator. The half of 3/2, 1.63, 2.63, and two lots of 2, add 2.6, 2.46. And that should get you this result here. Hang on. 2757 over 200. And you put that as decimal if you want, that's completely fine. As a decimal, that would be 13.785. But obviously, A level, we love fractions, right? Just leave it there. Okay, so that's the result. Cool. CHPs involve having to prove n is real and non-infinite. Makes life so much easier. Yeah, like numerical analysis. Yeah. Always have to consider like the error bounds, stuff like that. Oh god, that takes me back. Okay. So part B then, we have to use that answer to part A to estimate these interval inequalities, right? These inequalities, what's that? Integrals. So 9 of 3 of log 3 to the 2x to the 10. And hopefully what you recognize here, these are logs and the logs, so we have to use log rules, right? And so really there's two main ones. It's going to be like a power one, right? Power one, so it's going to be a to the m. It's going to be like n. That's probably what most people use. N log a, and then we've got the addition one. So if we add two together, and obviously there's a subtraction one as well. But let's just consider this one first. Okay, so which of these two is most likely? Well, we have a index staring at us, right? So I think we're going to have to apply the index one. So we bring the power to the front. So it's going to be an integral between 9 and 3 of 10 log 3 to the 2x. And what do I notice here? Well, I can bring the 10 out. And then what do I notice? It's the exact same integral we had in part A. So that'd be 10 lots of our answer. So it's going to be 10 lots of this fraction here. Which would be 2757 over 0. Well, that'd be over 20, right? And that's the sort of thing, right? So it's a fairly common sort of exam question to use log rules to simplify stuff, and this will it will come up in paper too. And they might combine it again with trapezium rules or something. So yeah. It's okay. It all tends to about 3 by real analysis. Oh, okay. I don't know. I can't remember that far back now. uh, um. Okay, so we have part II, and now we have to somehow find something with this interval. So 9 and 3 of log 3 to the 18x dx. Okay, so again, that goes back to the two sort of log rules, right? Do we have a power? Well, not really, no. There's no power here. So the only other way we can kind of do something with this is by somehow forming a product. And I recognise we have a product here of 18 and x. But I need the 18x to go to a 2x, right? In order to then use our original integral. Well, how are we going to get 18x to 2x? Well, I reckon it'd be 2x times 9, right? So then I could say that's between 9 and 3 of log 3 of 2x times 9 dx. Um, and then we split this up, right, using the integral. So that's between 9 and 3 of log 3 to the 2x add log 3 to the 9 dx. And so what I notice now, again, I can split this into two different integrals because they're adding. So it'd be 9 3 of log 3 to the 2x add the integral between 9 and 3 of log 3 to the 9 dx. Now, actually, this integral again is what we had in part A again. So that's the whole idea, right? Keeping part A in mind, try and get that what did you call inequality? Integral, uh, and then that's what we got here. So actually, this is our part A answer again. So that's going to be 2757 over 200. But actually, this although looks a bit nasty, it's just a constant, right? Because these are all definite numbers, log 3 to the 9. You can actually put that into the calculator if you wanted, but really recognise that log 3 to the 9, although you don't have, again, you can put that into the calculator, but that will be 3 squared, right? And then I can bring the 2 out, and then log 3 to the 3 just goes to 1, so then 2 times 1 will be left with 2 dx. If you are a bit, if you feel a bit weird dealing with logs like this, you can just put that into the calculator. If you know it's a number, obviously you're not too sure what to do with it, it's fine to just put it in the calculator, really. But that's the step, right? Anyway, so that's between 9 and 3, 2 dx, and actually we know how to integrate this very nicely, right? So that's going to be 2757 over 200, and now that would be 2x, right? And it's between 9 and 3. And then if we evaluate that, 2725 over 200, add 2 of 9 minus 2 of 3. So remember, they substitute the upper limit and then subtract by the lower limit. And you put that into the calculator, you get this number here, this fraction here. 5157 over 200. That's it, right, for that question. So hopefully you can start to see there how you sort of apply the log rule to simplify stuff, which again will be a very important skill, I reckon, for paper 2. Um, so yeah, hopefully that made sense, hopefully. So yeah, I guess the main takeaway is, again, for A, use the formula to help you find an n here, the number strips. So you know the first point has to be y0. Then you can count up to find the last point, which is y4. That means n has to be 4, because obviously the final point here is n. Okay. And as for the log rules, if you have an exponent, like I said, that should be fairly clear when you use an exponent. But if there's no exponent involved, then you're probably gonna have to make some sort of product, right? Or division or something, to then simplify stuff. But okay, hopefully it made sense. I'm gonna move on now. Question 3. Cool. Oh, uh, and I reckon this could happen, right? So we have a differential equation mixed with partial fractions. So I reckon that probably could come up. So let's have a look at it. So part A, express 3 over 2x minus 1, x plus 1 as a partial fraction. Well, that means essentially a partial fraction. Hopefully, you practice this. You're splitting up each into like a separate, a linear denominator. So denominator of only one factor, right? So the whole idea is if you factorize it, and then you split up all the factors into different fractions. That's essentially what's going on. So we have a over 2x plus 1 plus b over x plus 1. Okay, and let's make it a bit clearer. Okay, so I need to point A and B. I reckon, let's try and add it. So ax plus 1 plus b 2x minus 1. So I'm just adding the fractions together to get common denominator, which again will be x plus 1, 2x minus 1. And I noticed this is in the exact same form as the original fraction, but the denominator is the same. So that means the numerator also has been the same, which means we get this. And now this is essentially some sort of simultaneous equation, and you can do this many ways, right? To find A and B. I think perhaps the best way is to set each bracket equal to 0, because what that will ensure is that you get rid of all the constants, right? So you only have one equation with one constant. That's easy to solve, right? So the first one, let's let this bracket equal to 0. So that's going to be x plus 1 equals 0, so x will be minus 1. So we sub that in. My 3 is just going to be 3 still. And 3 will be a lots of 0, which will just be 0. And then b of 2 lots of minus 1 and minus 1. That will be minus 3b. So therefore b would be, minus 3b is equal to 3. So b would be minus 1, right? Okay. And then we do the same for the other bracket. So 2x plus minus 1 has to be 0. So that means x has to be a half, right? So therefore 3 would be a lots of a half plus 1. And then plus b, well 2x minus 1 will go to 0, so that's nothing. And that would be a half plus 1, that would be 3 over 2a. Well then therefore a has to be 3 divided by 3 over 2, which should be 2, okay? And there we are. So now we found our values. So then as a partial fraction, what was it? The original fraction of 3 over 2x minus 1, x plus 1, is going to be a lots of 2x minus 1, was it? Let me double check. Yeah, a over 2x minus 1, so a was 2. And then add b, which would be, well, add minus 1 over x plus 1. But obviously, the minus can be brought out, so it'd be minus 1 over x plus 1. And that's your partial fractions. Okay, cool. So part B, then we are given the big block of text. Don't get bogged down by the words, right? But really, all you got to factor it. The only thing that's really staring at me right at the moment is this differential equation here. And immediately I'm thinking, I'm probably going to need to solve this. And actually, I do. So really, I just need to solve this equation and ignore pretty much all the words, right? Perhaps no, not V and TR might help, but we can deal with that when we get to it, okay? So let's just solve it then, right? So we have dv over dt is 3v over 2t minus 1 t plus 1. And with A-level math anyway, we essentially separate all the variables, right? So that means one variable has to be on the one side, so we're going to have to times by dt, right? So that's the first step. dv is going to be 3v over 2t minus 1 t plus 1 of dt. That's always going to be the first step, right? Unless obviously you're very confident and you can do it all in one. But that's the first sort of approach. Get rid of the dt. And so then I've this on one side and the other d on the other side. So I need to get all the variables as separation of variables hints. We need to get all the one variables, so the v has to be on this side, and all of the t's on the other. So we have 3v on here. So how are we going to get rid of v? Well, we're going to divide by v, aren't we? To get rid of the v on here. So therefore, divided by v, we'll get 1 over v dv. Obviously then, because 3v over v will cancel out. Okay. And then that'd be 3 over 2t minus 1 over t plus 1 dt. And now all the t's on the other side as well. Cool. And so because we have this dv stuff here and this dt, that means we can integrate, because obviously an integral has that dx bit at the end. We already have that d bit, so we can actually just integrate both sides. So 1 over v dv is the integral. I'm going to bring the 3 out, actually. I don't like having multiples in my integrals. I don't know. But that'd be 1 over 2t minus 1 over t plus 1 dt. And so actually, I should now be able to integrate both of them. Well, 1 over v is sort of like the reverse chain rule, or like the log rule, essentially. So 1 over v will be, the integral will be ln of mod v. Okay. Pay attention to the modulus here, because v could be negative or vice versa, with the t or whatever. But it has to be a modulus, because obviously logs aren't defined for negative, so we have to account for that. Okay, because our original function, right, our original value of v is not modulus, right? It could be a minus, and that'd be fine. So then if we then do some integration, we have to account for that possibility by adding a modulus. But don't worry about that too much. You just need to know we have to have a mod v. The reason for that, very briefly as well, it's because this reverse chain rule sort of situation here. So if we have the f of x and we have f dash of x and some lots of it on the top, if this differentiates, v differentiates to 1, doesn't it? So actually, then the integral will be the log of the bottom function, which should be v, and that'd be mod v. So that's briefly where that comes from, right? But yeah, that should be. I hope you practice stuff like that now. Anyway, hopefully that shouldn't be too bothersome. So then we have 3 lots of this, and actually, I don't really know what to do here. Obviously, hopefully you should spot it though. But I know this split up to partial fractions because, like I said earlier, we have factors in the denominator, so that means we can split it up, and that's what we've done in part A, right? We have this expression here. So 3 lots of 2x minus 1 is this. So if I just bring the 3 back into here, say, that's exactly the fraction we split up into partial fractions, right? So then we can say 3 lots, or all of this is these 2 fractions here. So we just substitute that in. So we're going to have 2 over 2t minus 1 add, no, it's minus, wasn't it? Minus 1 lots of t add 1 dt. Okay. Oh, no, that should be in t's as well, not x's, sorry. T plus 1t is 2t minus 1t. There we go, not x's. Okay. But then in the same sort of principle, I can then use the log, it depends what you call it, reverse chain rule, log rule. So I recognise 2t minus 1 differentiates to 2. So actually it becomes, so ln v equals, and this becomes log or ln of mod 2t minus 1 minus, and then t plus 1 differentiates to 1, which is exactly what we got. So it's exactly ln of t plus 1. And there will be a plus c, right? Because it's indefinite integration. There's no limits on any integral. So we need to account for plus c. Okay. What I then know is I can bring the logs in together. So tt minus 1 over t add 1, because we have this minus here. So again, remember the log rule, log a minus log b equals log a minus b. I might not be able to do anything with that, but it's staring at me in the face, and maybe it'd be useful. So I'm going to do that, plus c, okay. Okay, now to find plus c, I believe we are given some information. So it's exactly 2 hours. T's in hours, right? So that means T equals 2. Total volume of 3 of oxygen. Well, V, where's V? The total volume of oxygen produced is V. So actually V then would just be 3. And so we're going to solve it, right? So then we're going to say T is 2, V is 3. Then we're going to substitute that in to then find C. Okay. I'm not gonna. You could try and not make it a lot more presentable to then get V on its own instead of log V, but then have this plus C, so it makes it a bit fiddly. I think I can find C straight away, right? So V is 3. That means log 3. So mod 3 is obviously just 3. It's going to be log of 2 lots of 2 minus 1. Let's make it over 2 add 1. So I'm substituting t's 2 in. So that means log 3 has to be log of 2 times 2 is 4 minus 1, which should be 3 over 3. That's going to be log 1. And then log 1, you can put that into the calculator, but it's going to be 0, right? So that would be 0 add c, which means c is simply ln 3. So then I can bring this back in to say ln v now has to be ln of 2t minus 1 over t add 1 plus c, which is ln 3. Now actually, again, I can use the other log rule, which multiplies them together. So log AB is log A add log B. So I've got two logs added together, I can bring them in. So then say ln mod V is ln of modulus of 2t minus 1 over t add 1 ln 3, 3, sorry, times 3. You can bring it in even though this one is 3 is not a modulus, because of the fact 3 is positive, right? So it wouldn't affect it at the end of the day. So you can do that, okay? And so that becomes ln of 2t minus 1. Rather, that'd be 6t minus 3, wouldn't it? Over t add 1. I just times 3 on the top bracket. And so that's equal to ln mod v. But then I can clearly see that the inside the logs have to be the same, right? So that means v has to be 6t minus 3 over t add 1. Cool. You may be no, actually, never mind. And yeah, that's what we get. I think. Let's check what they wanted. Oh, it should be 3 apparently. Uh, Interesting. Okay, so I'm off by a factor of 2. So they got 3 lots of 2t minus 1. I got 6. Why is that? Oh no, that's the same. Of course it is. I've just expanded it. 3 2t minus 1 is 6t minus 3. Oh my god. There we go. I don't know why that's. Oh god. So therefore we could say that that's log of 3 lots of 2t minus 1, just to make it very clear, over t add 1. And then therefore the logs inside have been the same. So that means v is 3 lots of 2t minus 1 over t plus 1, which is what they got. Yes, okay, there we go. Lovely. Okay, then we're going to do part C. I'm going to do part C over here. I don't have much room. Then it says the scientists deduced there was a time delay between the chemicals being mixed and oxygen being produced. So remember, V is the oxygen produced. So if there is a time delay, that means that obviously V equals 0. And what's essentially going on there is if there's a time delay between oxygen being produced, that means when like V is 0, so here, right, that's V0. Um, there's like this little uh, delay before the V starts going up, right? Something like that. So that delay before the V starts jumping up or moving up or down or whatever, but it's going to go up, right, because it's volume. That is the time delay. And it says the limit. I'll talk about the limit in a second. So then it says on the time delay. So again, the time delay is when V is 0, because obviously there's no oxygen produced. So again, bear in mind V is 3 lots of 2t minus 1 over t add 1. We need V 0, right? Now when V is 0, obviously this whole fraction is equal to 0, right? Because that's V. Now, that means the numerator has to be 0, 3 lots of 2t minus 1. Again, if you're a bit unsure with the denominator, you could just times across. So 3 lots of 2t minus 1 is 0 lots of t add 1. But 0 lots of anything is just 0 still, so it's just the numerator equals to 0, okay? But then 3 lots of 2t minus 1 equals 0, but then we could just divide by 3. So then 2t minus 1 equals 0, which means t is a half. So that would be our time delay, right? So it goes up to t is a half before it starts going up, okay? Now t's in hours, so a half of an hour is 30 minutes. Okay. Yeah, it says give you answer in minutes, so yeah, I need to make sure of that. Then it says the limit, so it's talking about the limit to the total volume of oxygen produced. So that means no matter how long it takes, there'll be no more oxygen produced. That means we need to consider when t goes to infinity. Now, I did speak about this before, but I'm not a big fan of of this sort of thing in normal math because they don't really teach limits like that. But essentially, there's two ways you can do it. So again, V is this here. We need to see what happens when t goes to infinity. And it's not immediately obvious because there's got t's on the top and the bottom, right? It's not immediately obvious where that goes. The one strategy you could is to plug in a very, very large value of t and see what happens there. Um, so you could say t is like a billion or something. So if I did like a billion, 3 lots of 2, so that'd be like t is uh 10 to the 9, wouldn't it? Um, it doesn't matter. We need a large value of t. So if you just plug in 10 to the 9, for example, or 10 to the 20, or whatever, some really large value. Um, 3 lots of 2 of 10 to the 9 minus 1 over 10 to the 9 plus 1. You get v is 5.999, and it really lots of nines, and it goes to an 8. So clearly that's going towards 6, right? And that would be your limit there. Okay, so v would be 6 is the limit, okay, of oxygen produced. Which we can deduce from the fact it's very clearly tending towards that sort of number, right? 6. The other way, and the more formal way, is actually, well, if we expand the bracket, we're going to have v is 6t minus 3 over t had 1. Now, if we actually divide by t or times by 1 over t on both the top and the bottom, we're going to get 6 minus 3 over t add 1 over t. Now, what you do need to recognise is 1 over t, when t goes to infinity, this goes to 0. Right, and again, you can even say that with like a reciprocal graph. Let me scroll down. Reciprocal graph. So obviously, as t goes to infinity, 1 over t goes to 0. Or again, just try some numbers and see what happens when t is very large. When you recognise that, that means v alternatively, when t goes to infinity, that means 1 over t goes to 0, and then you can substitute that in to say that's going to be 6 minus 0, right? So 6 minus 0 over 1 plus 0 is 6. And that is your limit, okay? So that's the formal way of doing it. And hopefully that showed you. Hopefully it made sense. That's the proper way. But if you are struggling, stuff like that with limits, they don't teach it very well. So I don't think they make it too complicated. So you can just try and plug in some large values, right, see what happens. But yeah, so that's that question. So therefore, limit is 6 meters cubed. Cool. Okay, that's question 3. Um, so again, be prepared to like mix with partial fractions at other parts with differential equations and stuff like that. You never know. There might be a very similar question. This was from 2022 paper 2. So you never know, based on the trend from paper 1, it might be a very similar question. So hopefully now you've seen all like the different bits to it. Okay, we have question 4 now again from paper 2, 2022. And so we are given a function f, which is defined as this. We need to find f inverse of 3 over 2. Okay. Again, there's two ways to going about this. Recognize either x, y, if you the inverse function, then the coordinates would be yx. So y is like the input of f inverse. So f, and that's f inverse. Y can't, they switch roles. Right? That's the whole idea of an inverse function. So what that's saying is, if that input's 3 over 2, y would be 3 over 2. Therefore, you're solving 8x plus 5 over 2x plus 3 equals 3 over 2. And then you find the value of x, right, that gets that. I'm going to do part A here, yes. Alternatively, and this is the way I'll do it, because I think a lot of people would be more comfortable in doing it this way, is to simplify the generic function, f inverse, using what you know, by saying y is f of x, so y would be 8x plus 5 over 2x plus 3. Then you rearrange to get x in terms of y again, because they switch roles. So that means we have to rearrange to get x in terms of y instead. And that's your inverse, right? Then you can just plug in 3 over 2. Okay, let's do that. So again, so the first step really is to get rid of the fractions, so times by 2x plus 3. And that'd be 8x plus 5. Let's then expand it. So 2xy plus 3y equals 8x. Add 5. And then I want x is on their own, so it's 2xy minus 8x is 5 minus 3y. Then I can factor an x out, say 2y minus 8 is 5 minus 3y, and therefore x is 5 minus 3y. 2y minus 8, I've now switched them around, so that means the inverse of x would be 5 minus 3x, not y, remember x, in terms of 2x minus 8. And then I can just say, to then find f inverse of 3 over 2, that will be then substituting 3 over 2 in. So it'd be 5 minus 3 of 3 over 2 over 2 of 3 over 2 minus 8, and that will get you minus a tenth. Okay. And then part B. Says now we need to show f of x can be expressed in this form here. And again, there's two ways of going about this. And either you could do it directly. So again, kind of like partial fractions. You could either just combine them together. So you could say that's a 2x plus 3 plus b over 2x plus 3. And so the numerator has to equal the numerator here because the denominator is the same. So that means a of 2x plus 3 plus b would equal ax plus 5. Then you do the normal sort of method, like partial fractions, like that we did earlier. You could substitute two values of x in to get a and b, or compare, or do whatever, and then you can find a and b that way. Alternatively, you should actually spot this is a top-heavy fraction because the degree of the numerator is at least the degree of the denominator. An algebraic fraction should always have a denominator of a higher degree of x. But here they're both degrees of 1 because it's a linear. So actually what that means is we should be applying long division here. So if we apply long division, that's saying 2x plus 3. And either method's fine, by the way. It's not like you only can only do one, right? The mark scheme will always award as long as it says, for example, if it said by using long division, you have to use long division. But if it doesn't specify any particular method, you can use any valid method, right? That gets you the answer, and you show your work, you'll be fine. So either method or whatever else is fine. But then if we carry out this long division, 2x plus 3 of 8x plus 5, then we need a number that times by 2x to get 8x, right? So considering the first highest power of x, they need to match. So that would be 4, right? And then 4 times 2x is 8x. And then 4 times 3 is 12. And then we have to minus from each other. So then 8x minus 8x is 0. And then 5 minus 12 is minus 7. So therefore, that means the quotient, so f of x is that. And so the quotient be 4, and then the remainder is minus 7 over this 2x plus 3. And that means clearly a would be 4 and b is minus 7 here. Okay. But if we then compared it again, like we did earlier, if we then compared it with if you did the comparison method where you added the fraction and then you looked at setting values as some values of x to 0 or whatever to match with the numerator here, you should get the same values of a and b. Okay. But yeah. Then we say part C. So what's part C saying? And then the function g is defined by g of x is 16 minus x squared between 0 and x and 4. State the range of g inverse. Okay, so I immediately notice it's one mark and it says state. So that means without to do any working really. So I should be able to just see it. Okay, so the range of, but it's saying the range of the inverse function, and we're given the original function. And what you should recognize is this is the same as the domain of the original of g of x, right? Again, the reason why that is because of the fact that x and y's switch, right? They switch roles when it's f and f, the normal function and the inverse function. So that means the domain of the original will go to the range of the inverse and vice versa. So then we just need the domain of g of x, but we are given the domain. This is it. It's the values of x we can use, right, at input. So actually, it's between 0 and 4, the range. So we can spot that the range is g inverse and between 4, not x. Yeah, it's the inverse function g of -1. Okay. Then we have part D. Then it's asking for the range of fg minus 1. Now, you should recognize again, this is a composition. This is saying f of g inverse of x. So that means the domain of f, or the input of f, is actually the g inverse of x, okay? So then to work out the range, we need to work out what input f can take. But we already said that g inverse can only be between 0 and 4. So that means we need to consider f of x between 0, x, and 4, right? That's really the range between when x is 0 and 4. So then let's consider the endpoints then. So f of 0 and f of 4. So f of 0, so f of x, remember, is, well, we worked it out in part B. It was 4 minus 7 over 2x plus 3. So then f of 0 then is going to be 4 minus 7 over 2 of 0 add 3. And that will be 5 over 3, right? Likewise, f of 4 would be 4 minus 7 over 2 of 4 add 3. And that would be 37 over 11. Cool. So then you'd probably be, and so that's cool. So it's between 0 and 4. So the last thing we need to check is if if the function's increasing. So obviously 5 over 3 is smaller than 37 over 11. So say 5 over 3 is here for f, for our range for 0. And then at 4, it's 37 over 11. So it goes from here to say here. We need to check there's no turning points, or in other words, we need to verify that it's an increasing function, right? So that means there's no jumps like this, right? Because of a turning point, there's a value that goes out of the range between 5 over 3 and like 7 over 11, right? It if there's nothing that goes above 37 over 11, which would happen if there's a turning point, right? Or likewise, it could go beneath, or and stuff like that. The only way it can go like that is if it's increasing. So that means for every value of x, as x goes higher, the function always goes higher. So that essentially bounds it between 37 over 11 and 5 over 3. So we just need to see that it's increasing. If you were stuck, this is probably quite complicated, right? It's quite what's it, abstract to see this. If you were struggling, you'd probably just say f of 0 and f of 4, and then just put these as your values, right? So f of 5 over 3 between f of f g inverse, right? 37 over 11. Actually, that is the right answer. If you are stuck, you can just do that, but you just also need to verify it's an increasing function, and you can see that because of part B. So remember, we defined our function to be 4 minus 7 over 2x plus, not to find it, sorry, we worked it out to be that, right, in part B. This means there's only one x there, which means there's only one place it varies. That helps us a lot because we can then just consider uh, where it varies, and then obviously work away from there. We don't have to consider like say like with originally in the original fraction, there were x's in two places, so we kind of have to somehow like balance and like juggle the x varies in two places. It's a bit iffy. It's kind of like we complete the square, right? If you just had a normal quadratic, I don't know, like 2x squared at 3x plus 4, it's very hard to see what the maximum is because x varies twice. We can't just like, you know what I mean? But if you then complete the square, I don't know what the complete square form of it. It's like 2 of, what was it, x plus 3 over 4 squared. Uh, I don't know what the other. It's just and a constant. Okay. We can then clearly see because x varies only once. We can kind of like clearly see where the maximum and any turning points are. That's the same sort of idea here to see where the range will be. Okay. So part B is useful because we only have what again only one variation because there's only one x. So what that's saying is, well, let's consider what happens to x. So when x increases in general, as x gets bigger, 2x plus 3 gets bigger, right? Then, because we're divided by a bigger number, 7 over 2x plus 3, that means the fraction overall gets smaller, right? Because, again, we're dividing by a bigger number, the denominator gets bigger. But then we're subtracting by the fraction, right? And because all these numbers are fixed here, again, the only thing changing is the x. So as the denominator gets bigger, the whole fraction gets smaller, but we're subtracting by a fraction. So as the fractions get smaller, we're subtracting by a smaller number as x gets bigger. That means this whole function overall gets smaller as x gets bigger, sorry, as x gets bigger. Because we're subtracting by a smaller number, that means we're taking less off the 4. Okay, so that means that as x increases, then the whole fraction gets smaller, so we're subtracted by a smaller number. So actually, we get a more positive answer, and so it's increasing. Okay, because of that sort of logic. Therefore, because it's increasing, it has to be between uh, the point 0 and 4, right? There's no weird jumps because of the fact we already considered it's increasing for all x, right? It doesn't go, if we had a maximum, right? For example, if it jumped up, that would say it would be going down at certain points as well. But it's not decreasing at all because of what we just discussed. It has to be always increasing, so it has to follow exactly this sort of shape. Okay, it has to be an increasing function because of that. Therefore, it has to be between 5 over 3 and 37 over 11, our two limits, right? So therefore, we can essentially prove and verify it is indeed 5 over 3 and 37 over 11. That's where the range is between. Okay, that is very, very complicated. You do not get any marks for that, by the way, for considering or proving it's increasing. But you do have to check it, right? But for A level, it's not going to be too bad. Again, like I said earlier, if you are unsure, just like write the inequality down, right? And you'll get most of the marks, right? Even if it's not that sort of way. Uh, but yeah, that I know that is very tricky. It's very analytical. You have to think very, very deeply about that, and that can throw a lot of students off. I am aware of that, but you do have to prove it. You have to basically rule out the fact there's no turning points. If there are no turning points, then that means there has to be an increase in function, right? To avoid the fact there's no jumps, right? And if there is a jump, that means it has to come up and then it has to come down. So it'd be decreasing at certain points. So we have to rule out the fact it doesn't decrease, essentially. Okay. I'm gonna leave that question there. Then hopefully that made some sort of sense. I know that's very complicated. Um, but yeah, the mark scheme just essentially jumps from f0 to f4 to this right inequality. Like I said, you get no marks for considering the fact it's increasing, but you do have to consider it, right? Um, but yeah, that's I know range is what a lot of people struggle with. I don't have much to say there, unfortunately. Other than I don't know. Other than it won't be too complicated. Hopefully, they'll be fairly simple with it. Okay, like I said here, you just plug in. In this case, all you have to do is really just plug in the two endpoints, and then there's your range. Okay, let's move on. Question 5. Cool. So this is logarithmic modeling. Because obviously we have a model given here, and it's with a log. Okay. And this could come up as well. Okay, so we'll let me scroll down actually. So we're given this graph, we're given 2 points, and we turn the value in pounds and in t in months. We're given this formula, this model, right? V is AB to the t, and it's a linear relationship between log V and t. It's linear, meaning it's a straight line, right? Then it says it passes through these 2 points, which we see on the graph. Then we need to find the initial value of the phone. So that's going to be when t is 0, and we need the value v, okay? Not log 10 of v, but v. So that if we plug in t, let me do part A then. Well, if t equals 0, then v is going to be a b to the 0, which is going to be a. But we don't know a, so we're going to have to work that out. But we know a, we know log 10 of v and t. We know that we can't substitute these points into here because this is log 10 of v. This is not v. Well, then we're going to kind of have to take logs then, right? So we're going to say then if v is ab to the t, therefore log 10 of v is going to be log 10 of ab to the t. And that's going to be always the way you tackle these questions. When you're given a log sort of model like this, if the graph's in logs, you're going to have to take logs on the equation, right? This is essentially linearizing the graph. And you can see because it's now linear. And that's the strategy. Always take logs of your equation if it's given in logs in the graph or the model. Okay, so now we can use log rules to separate this. So again, I know we can say it's log 10 of a, add log 10 of b to the t. Hopefully you can see that right. That's just log rules. So if we have a product, again, we can split that up into an addition of two different logs, and I have a power of t. So now I can say that's t log 10 of b. Now I can substitute a point in, perhaps, to find a. And I'm going to substitute this point, I think, because we have a 0, so that's always going to be nice, right? So again, t is 0 now, so that means log 10 of v. Well, we know what log 10 of v is, don't we? We know that log 10 of v is 3, right? Because remember, this is this point here, and this point is on it's on log 10 of v. Okay. So that means log 10 of v is 3. Okay. Hopefully, the main point here is to recognize the distinction between v and log 10 of v, and why we cannot substitute these points into this equation. So we have to substitute it into this log equation instead. That's why we take logs, so we can substitute these points in. And then we can convert between log 10 and v by taking exponentials or logs or whatever. Okay, so now we have this. So then we can say no, log 10 of that's 3. That's going to be equal to log 10 of a, and then add t, which is 0, log 10 of b. But anything times 0 is 0, so that is all just log 10 of a. Well, we need to find a, but we can find a. Because then if we raise by power 10, that means 10 to the 3 is 10 to the log 10a. And they cancel because they're inverses, right? If you want to think of it that way. So that means a is simply 10 to the 3, which is 1,000, right? 1,000. Well, that's our value then. Therefore, the value v, not log 10 of v, but the value v, remember we discussed here the initial value v is a. That's going to be 1,000. Okay. Cool. Okay, hopefully that made sense. But yeah, I think that's probably the tricky thing here. Then part B. Then it says to find a complete equation for V here. So we have to find the missing values A and B. But we know what A is already. A is 1,000. So we just need to find B now. Well, we are given another point on this line here, aren't we? We're given another point that lies between log 10 and V and T. So I think we can use the equation we found in part A, right? So remember, if we take logs on both sides, log 10 of V is going to be log 10 of A, but A is 1,000. Now, if you remember, 10 cubed is A. So that means we could just move it to the front, so 3. So then log 10 of 10 is 1. So then you're left with 3 times 1 is 3. If you are unsure of that, just plug in log 10 of 1,000 in the calculator. You'll get 3, okay? If you are unsure about stuff like that, you do have to calculate to help you out there. But I'm just showing you why you can get to 3. Okay, so that's going to be 3 then. Add t log 10 of b. And then I can substitute this point in because now I have t and log 10 of v. So I know that t is 10, so log 10 of v is going to be 2.79, okay? Therefore, 2.79 is going to be 3 at, at 10 log 10 of b. That now I need to solve this for b, right? Um, the first thing I'm going to say is about 10 log, oh, 10 log 10 of b, lots of tens. 10 log 10 of b, that's going to be 2.79 minus 3. And that's going to be minus 0.21. Then I can divide by 10 to say log 10 of b is, if I divide by 10, you get minus 0.021. Then again, I can solve for b now by taking tens on both sides. So 10 log 10 to the b, and again that will be just b because again the 10 will cancel the log because it's a base of 10. And so you're left with b will be 10 to the minus 0.021, which should be what is it, 3 significant figures here. B would be 0.953, the 3 sig figs, okay? Cool. So now we found V. We know A as well. We know B. Then it said to find a complete equation for V. Now, what that means is we need to rewrite the equation, but plug in our missing numbers, right? So A is 1,000, as we see here. So 1,000 B, which was 0.953. Oh, let me write to the T, and that would be your model. Okay. Okay, cool. Then we are given exactly 2 years after it was bought, the value of the phone was 320. Use this information to evaluate the reliability of the model. So this is very typical, right? They give you some other piece of information, and then you need to substitute that into the model to prove how reliable or close it is to the true answer. So the value is 320, and T is 2. So you can do two things. You can either plug in 320 with V and then solve for T, or the far better way, then you have to take logs, right, or whatever. You can just plug in T 2, and then you just get V straight away. So T is 2, that means V would be 1,000 of 0.953 to the 2, and that would be it's T in years, by the way. I need to check this, by the way. Yeah. Oh. T's in months. There we go. Because I got an answer of 907. That's not particularly right. See, I need to check the question there. Yeah. So with this modelling, what you should always pay attention to is the units, right? So T, you need to check them. It's in months. This is in years. So that means T is 2 years. No, sorry. T would not be 2, but 2 years is equal to 24 months, right? So that means T is 24, and that's what you substitute it in. So 24. There we go. So 1,000 of 0.953 to the 24. That gets you a lot of a more sensible answer of 314.94. Okay, in pounds. So that's our answer. But actually, it's very, very close to 320. So I think it's quite reliable, right? You can calculate percentage error if you wanted to be really sure. So you could say, well, again, so 314.9294 times our multiplier, so a percentage, increase or decrease. It's a percentage error, right? That has to give 320. X would be 320 divided by the answer, which should be 1.016. Therefore, times by 100, it'd be a 1.6 percentage error. Okay, that's very, very. I think that's very good. Really, less than 1% error. No, not less than 2% error. Sorry. Stats in significance level, for example, like you used to 5%, 10%. That's basically the error of margin, right? And normally, if it's below 5%, you accept, the like null hypothesis. Here, because it's like below 2, you can kind of accept it's a good error. So it's a good reliable, it's a good approximation, right? You don't have to put the do percentage error. You don't have to do that, right? I'm just showing. You can be really, if you feel a bit like I need to be a bit more rigorous or precise, you can do it that way. But in general, notice it's really bloody, it's really close, isn't it? So the answer is yes. And the thing is as well, you really have to be, you have to appreciate with these modelling stuff. It's not perfect, right? You're not going to get perfect answers. You're not going to expect your answer to be between like 319.99p. Okay, you have to be a bit more open-minded than that in reality. Um, so an answer close like this is still pretty good, right? Um, Only when you get to say something, I don't know if it's like 200 or something, then it's a bit off, right? It's not as reliable, but because it's only a few pounds off, it's not a big deal. So you kind of have to be a bit. You shouldn't be stringent with these type of things, right? As long as it's in the ballpark and you're not too pedantic, essentially, about how close it is to the answer. You have to take that into account. So because it's not really that far away, it is a good approximation, right? So uh, the model, therefore, is reliable. So reliable, obviously, again, doesn't mean it has to be like perfect. It doesn't have to be spot on or like off by like a decimal point. Just have to be reliable. So you can use it to get like a sort of ballpark figure, right? Which is what we got here. So the model's reliable as it predicts the value to be 314.94, which is close to 320, right? And that's essentially your reasoning, okay? Actually, funnily, I did check the mark scheme as well. And actually, they do not accept in this particular case if you say no. Okay. Normally, they do say you can have yes or no depending on your reasoning, but here they've said straight up you can't say no. You have to say it is reliable. Again, so it's saying like you do have to be quite open-minded and flexible with how different the answer is. You know what I mean? So you can't say I was off by like a decimal point, so therefore it's not reliable or whatever like that. You do have to be quite, and the examiners expect you to be fairly open-minded with your answer. Okay. But yeah, so that's really all it is. So again, the main central point, again, if you get a question like this, you just need to take logs, okay? If and an equation like this, if you have a graph that's in logs, because then if you have it in logs, you can then substitute any points of information you're given. Because remember, this is v, but this coordinate only works for log 10 of v when v is logged. Okay, so you have to take logs first, and then you can substitute the points in. Okay, cool. Question 6. Okay. How many questions I put in that? 15. I think some of it might be on to the next session, I think. Anyway, question 6. So, again, this is very typical. Every year you get like a sort of first principles question. I think most people like it, right? But again, it's better to go over it. Either they can give you sine or cos, or they will give you some sort of like x squared, x cubed plus 1 or something like that. Some sort of like polynomial. But probably in the harder cases like sine and cos, and that's what I've got here. So we're given y sine x, and we need to show the derivative is cos x by first principles, and we're given this information here. Usually we'll give you this, right? You can sort of see it. By the way, I'm not going to go too much into it, but if you essentially use, and this isn't a proof, but if you use small angles, you should know sine theta goes to theta. So then that's essentially saying sine h over h goes to h over h, which cancels to 1, which is what we've got here. Because remember, h has to be small, theta has to be small. Likewise, with cos h, that would go to 1 minus a half h squared. But then in here, cos h would be 1 minus half h squared. But actually, h squared, when h is at 0 pretty much, this will pretty much be negligible. That will go to 0. So you're left with 1 minus 1 over h, which is 0 over h, which is 0, right? Which is why we got that result there. That's not the proof, but you can use it to help you see those. But they will give you the results, right? But I'm just showing there they don't come from nowhere. Okay. Hopefully you'll be comfortable with that now, and obviously the double angle which I've got here. Anyway, so that's just the waffle they give. So let's do it by first principles. So again, the first principles formula is given to you in the formula book. You don't have to remember it, but like with all formulas, you need to know how to use it. Okay. So that's our first step. So say if we call this f dash, not f of x, sorry, to make it match this, right, the f dash. Therefore, by using the formula, I can say f dash of x then it's going to be lim, which means limit as h goes to 0, of f of x plus h minus f of x over h. Okay, and then I just substitute it in. So the input x goes to x plus h, so that would be lim as h tends to 0 of sine of x plus h, and then f of x is sine x, so minus sine x over h. By the way, it's just a good idea to put the lim here. Make sure you don't forget it. I think it, it's hard to say if they're going to be lenient and stuff like this. If you say forget your lim h tends to 0 somewhere. But it's a good idea to just write it, right? It's only a few like words, really. I don't know, but it's best to be safe, right? Anyway, so let's do that. Okay, so how am I going to approach it then? What can I do now? Well, in a way, the question gives you a bit of a hint. Sine A plus B means we're going to have to do something with double angle. And I got a double angle. Well, not a double angle, but I've got an addition and of two angles here, right? And so I'm going to expand it. I'm going to use this identity, which is in the formula book, right? And I've quoted it here. Sine A plus B, which is this, right? Here I've got sine x plus h. So let's write lim as h tends to 0. X plus h, if I almost put an x and h here, that's going to say sine x cos h, right? Plus, because if it's a plus here, it has to match the plus here, right? But the cos one, I think we go over cos one now. I'm going to leave that till the later question to explain that. But then it'll be cos x, right? Sine h. And then I'm going to, oh god, I don't have much room here. I'm going to rewrite it actually. Let's move it over here. That will be lim as h tends to 0. Sine x plus h will go to, as I said, sine x cos h plus cos x sine h. So all I've done here, by the way, is replace the a and the b in the formula with x and h, right? Then that's minus sine x, which we have here. And then that's all over h. Okay, so what do I do then? Because I can't really just cancel stuff out immediately. So I'm gonna have to do something. You're gonna notice I can factorize. So, I noticed I have two sine x's. Tends to 0. Sorry. So that's sine x, and I notice that'd be cos x, cos h. Sorry, and then a minus sine x would be minus 1 over h. Plus sine h cos x. I can't do anything with that, right? But that's the best I can do to factorize it, right? To simplify it. Then what I can do actually, like with fractions in general, really, I can split it up into two. So I can split the limit up as well. So then I can say limit h tends to 0 of sine x. Oh, it won't let me delete this. What's going on? There we go. I don't know what happened there. Cos x, sine x, sorry, of cos h minus 1 over h. Why am I splitting it here? Hang on, let me just split it here. Over limit h tends to 0 of sine h cos x over h. And I was saying now, why have I split it up like this? Well, I notice I have a cos h minus 1 and a sine h here. So I have a cos h minus 1 and I have a sine h on this side. So I'm going to want to split it up to use both of oh god, to use both of the results, right? That's what I'm doing here. Oh, sorry. And that's what I'm going to do. So now I can basically almost effectively substitute this in. So then, lim of h tends to 0 of sine x times by cos h minus 1 over h, which is here. So remember, h is going to 0. That's what this limit's doing. So as h tends to 0, this bit goes to 0. So that'd be times it by 0. And then lim as h tends to 0 of, well, sine h over h would go to 1. So that means it's 1 times cos x, right? Uh, there we go. Um, okay, cool. So I've used that, and actually we've got pretty close to the answer now. Well, 0. Well, 0 times anything will go to 0, so that's 0. And then you're left with this. Lim as h tends to 0 of cos x, essentially, right? Then get rid of the 0. But what's going on here is I'm changing h, aren't I? I'm saying h changes and goes to 0. But here I have an x. X is not related to h. So actually, I can just get rid of this limit now because changing h won't change this at all. So this would just be left to cos x, right? And that is your f dash of x, which we wanted to prove, right? So that's saying then, therefore, the derivative is cos x, right? Well, y sine x, and we've done it. So that's the sort of idea, right? So really, once you got to this point, you just expand it using the addition formula. Then you kind of try and factorize to get these two, and then just substitute the results in. Okay, cool. Hopefully that shouldn't be too bad. Okay, now we have question 7. And it's a quadratic modeling question, right? So what we're told. So again, given some information. I'm just going to note the variables, right? H meters, vertical height, and horizontal distance x meters. Okay. And I can see that here, x and h. Okay, so that's really the information. These bullet points here. So the balls hit from a point on top of the platform of a vertical height of 3 meters above the ground. It reaches a maximum vertical height, horizontal distance of 90. And the vertical distance of 27 meters, the horizontal distance of 120, actually. Oh, want to make it a tad bit clear. There we go. Okay, then we are told down here, given also that h is model of the quadratic function of x, I made that bold. Find h in terms of x. So this is again very typical. So you need to basically give give the formula for this, right? And it's a quadratic curve. So what's a general quadratic like? Going to look like, right? H of x or h. Let's just call it h. Well, it's going to look like ax squared plus bx plus c, right? And hopefully you can recognise that's a generic quadratic expression, right? So that means any function, any quadratic function has to look like this. Hopefully you can see that. That's basically kind of the main step, essentially. To realise you can just give a generic one, and then our mission is to just find A, B, and C, right? To find a complete model. Oh, didn't mean to delete it. I want to get rid of the underline bit. And that's what we're going to do. And we're going to use this information here. Firstly, we are given it's hit from a point on top of a platform of vertical height 3 meters above the ground. So that's kind of saying at the start, right, at this point here. And they've given it here, so h is 3 here. And that's when x is 0, right? So when it hasn't moved at all, it's at a point of 3 above the ground. So if you formulate this in maths, that's saying, well, x is 0, h is 3. So actually, let's substitute that in then, see what we can do. So that's saying 3. Well, if we substitute that's going to be a of 0, right? And b of 0, by subbing x is 0, add c. Well, that goes to 0 and 0, so that means c has to be 3. So therefore, we can rewrite our model to be h is ax squared and bx, and now we can add the 3 in. Cool. Now let's do the other bit of information. Then we are saying it reaches a maximum vertical height. Remember, h is vertical height after traveling a horizontal distance of 90. So we are saying when x is 90, h, not giving us the height here, but h is h max, right? So h is this maximum height, h max. How are we? What does that mean then? Well, there's two ways of approaching this. You could complete the square, because obviously we should know completing the square in a quadratic gives us information about the maximum, right? But I actually think it's going to be a bit messy to do it. What you could realise instead is actually we can differentiate, right? Because h max is a turning point, so h max obviously will correspond to the maximum, which is this sort of turning point here. So that's h max, and that's going to be obviously when x is 90. If we, it's going to be the turning point, so we could say dh by dx is going to be 0, right? So then we can differentiate it. But don't be afraid of the constants, right? dh by dx then. So differentiate x. So x squared will go to 2x, and then a would mean 2ax, right? Then b, well, x will go to 1, so it just be b. Okay, and that has to equal 0. But we also know that this occurs when x is 90, so we can substitute 90 in. So say 2a of 90 add b equals 0, but therefore 180a equals minus b, right? Because 2 times 90 is 180, 180a, then I move the b on the other side. Cool, so that's we've got one equation. Let's see what we can do with the other bit of information then. Maybe we get another equation to solve this, okay? Then we're given the vertical height of 27 meters above the ground. At the horizontal distance 120. So that's going to again be x is 120, h, the vertical height is 27. So that means h equals 27, x is 120. Therefore, if we substitute it into, again, this sort of generic quadratic expression we got, we can say 27 is going to be a of 120 squared add b of 27, no, 120, that's 120, sorry. add this 3, okay? And actually then I can just put these values into the calculator to simplify it a little bit. So 27 is equal to, well, 120 squared is going to be 14400A, and then 120B. And then add 3, but obviously I can take 3 away from both sides, so that'd be 24. So actually then I've got 2 equations to solve for A and B. These are simultaneous equations, right? So I can call that equation 1 and 2. Um, you could. Some mark schemes are quite finicky, quite fickle. Sometimes they let you just pull it into the simultaneous equation solving your calculator, and they'll be fine with that. But I do think you should play it safe, especially for 5 marks. Here, uh, just try and not solve. You know what I mean? Solve it manually. Yeah. If you are really struggling for time, then just put it into the simultaneous equation, solve and move on. You probably lose that most amount of mark right for showing you're working. Um, but I think to play it safe, you don't know what the mark scheme's going to be like. Sometimes they accept it, sometimes they don't. But here it's just best to solve it manually. But here we already know an expression for b. So b is going to minus b is 188. So that means b is going to be negative 188 by dividing by minus 1. So then I can substitute 1 into equation 2, right? To then get 24. It's going to be 14400A. Add 120 of b, but b is minus 188. So then that'll be 14400A minus, well, 120 times 180 gets you 21600A is equal to 24. I can simplify this, can't I? So 14400 minus 21600 is left with. Okay, we're back. I think we are. Yeah. So apologies about that. But what happened was I was in the middle of computing it with putting in a calculator, accidentally flung it into my laptop, and then that caused the laptop to just crash and reset because it's. Oh my god. Yeah, my laptop's very run down and sensitive. I don't know. I just noticed in some of the streams it gets a bit laggy towards the end because the laptop just can't process dealing with stuff and it's just quite run down. But yeah, that's oh my god. Okay, and what I'm gonna see is because at the moment it's 2 different streams, but for YouTube or whatever, I'm gonna see if I can combine it into 2 so there's not much of disruption. But either way, there's gonna be a bit of a gap between obviously what happened. But yeah, anyway, let's just get on with it. So 14400, I tried to fling it on my laptop now. Minus 21600A gets you minus 7200A is 24. Then I could just divide by that. So 24 divided by minus 7200 gets you A is minus 1 over 300. That does not have a nice decimal, so you have to leave that in exact form. So that's A. Therefore, B. Remember, B was. Oh, did it not write B anywhere? Oh, did it not save that part? Oh no, B's here. Sorry, B's minus 180A. So B's going to be minus 180 of A, which is minus 1 over 300. And then that's going to be 300. That's 2, doesn't it? 300. And that's going to be 3/5. Quite nice, right? So therefore we found A, B, and actually we found C earlier. So therefore put off, if we have to find H in terms of X through the complete model, like you should be drilled into your head now with this sort of question. You have to restate the equation again with the missing values. So A is minus 1 over 300 x squared plus B, which is plus 3 over 5 x. And then I think C was what was C? We did it up here. C was 3. Okay. So that should be your complete model. And it's very typical with modeling to get weird numbers like this, okay? That's okay as long as it's not too weird. Like if I got some mad like third decimal, then I've probably gone wrong somewhere. But here I've got a fairly nice fraction. But yeah, that's that for 5 marks. Cool. Then part B says firstly again, this is pretty typical to sub some values into your function to get some back. So firstly, the maximum vertical height. So you could think, well, differentiate it, set to 0, find x and h, but they already told us that the maximum vertical height here, the second part here, occurs when the horizontal distance, when x is 90. So really, we just have to plug in x is 90 in without having to do any differentiation or complete the square or anything like that. So when x is 90, h is minus 1 over 300 of 90 squared, add 3/5 90, add 3. Um, and that will be 30. Quite nice number. There we go. 30 meters. Okay. And then the second part says the horizontal distance travelled by the ball. So horizontal, remember, is x. When it from when it was hit to when it first hits the ground. Okay. So remember, hitting the ground is going to be when the vertical 0. So it's going to be the x the root, right? The x intercept, which again is fairly common to use the model to find the roots, right? So here the first when it first hit is 0 here, x is 0. Then we need to find this missing value of x, and so the distance will be this x minus 0. Well, it's just going to be here. Anyway, so we need to find the root. So then you can, again, like I discussed earlier, you could put it to the calculator, but if you want to be really safe, the best thing with this, instead of putting in a quadratic solver, you can kind of do both. So just use completing the square, which should be fairly quick. So x is going to be minus 3 over 5, plus or minus the square root of 3 over 5 squared, minus 4 of minus 1 over 300, 3 over 2a. Which is 2 over 1 is 1 over 300. So you just quickly write down the quadratic formula, so you don't have to bother with factorising or complete the square or anything. But then you can pull it into the quadratic solver, right? Because then that'd be the same value, right? But then you technically shown how you got your answer, right? Um, but yeah, let's do it. So minus 1 divided by 300. 3 divided by 5, 0.6 and 3. You get 184.8683 or at minus 4.868 But obviously you can't have a negative because it's a distance, right? But x has to be 0, so positive. Hence, horizontal distance. Does it say to what one to round it to? Give your answer to the nearest meter. So obviously that's in meters. So round it to the nearest whole number. So that's going to be 185, right? To nearest meter. Okay. Then what's part C saying? Um, the possible effects of wind or air resistance are two limitations. The model give another. Oh, this makes me laugh because I know every single time, and I'm a culprit of it. Everyone just loves to give air resistance as the limitation always, and it is fair. But I love that they just took that away from you because they're like even the examiners are so sick and tired of seeing everyone write air resistance. So you have to come up with something else. But actually, the other way thing you can always say is the fact that you can say, well, it's a flat surface, right? The ground is flat. But it's that in real life, it's not going to be exactly flat, right? It's going to be a little bit hilly. It's going to be like some, I don't know, like stumps or something like that. Like it's going to be quite elevated, and then I mean, then it'll dip down slightly. It's not going to be completely like flat, is it? Really, if you think about it, it's going to be like bumps and here and there. It's not be completely level, and that's your limitation, because then obviously that could affect where it hits when it hits the ground, because obviously the ground will vary at height and stuff like that, and it varies the maximum. It really does affect the values of the model, right? If it's not a completely flat surface, that is the limitation, and that is another one you can pretty much always copy in, because obviously it's very very hard to model the x-axis, which is going up and down. So you just model it as flat. But that is a limitation, right? If they will not let you say it's air resistance, then you can say that. So limitation, it's just funny that was. Limitation is uh, the ground, or the horizontal ground, I'll just say more specifically, uh, would not be perfectly flat, right? In reality. Uh, and that's really what to say, really. And then that would affect, like I said, the values, right? And then that would actually affect the way you can actually model it as a quadratic. So it is a limitation. Okay. You could say something really like, I don't know. I did see. I remember the mark scheme as well. You could say, would it be modelled as an exact quadratic curve? It might seem a bit obvious, because obviously, again, because of things like air resistance, it's not going to be like a nice curve, like symmetrical curve like this, right? Um, and also you could comment on the fact it could be like multi-dimensional, so it could be 3D, because this is assuming it's a 2D thing as well, because it's only X and Y. But obviously, in reality, it'd be like three different variables. You don't have to think about that really. Just that you can talk about air resistance and the fact the ground is completely flat, right? Those are the two typical limitations. Anyway, let's move on. We're on 10:30 now. Okay. Uh, okay. Now with this, some binomial expansion. Again, this comes up every year. Pretty similar. Um. Okay. So it says find the first four terms of the binomial expansion of root 4 minus 9x. And essentially that is actually using this formula here. This is the AS version, but this only works when n is a positive integer. So this little n here at the end, this n here, means the natural numbers. So 1, 2, 3, 4, which just means positive integers, whole numbers, right? But obviously we're going to have a surd and stuff, so it's going to be fractional. And pretty much always, at least for A level, you're going to have to use this formula, okay? But that's really all we're going to do. It's just formula work. But if we're going to use the formula, we're going to need to get it in this form here. 1 plus x to the n. So we need to get this surd in terms of that. Well, how are we going to do that? Well, we are going to just use surd index laws, right? So you can say root 4 minus 9x is going to be 4 minus 9x to a half. Uh, and then we're pretty similar, right? But um, it has to be 1 plus x, not 4 plus some lots of x, okay? So we need to deal with this 4, okay? And the way you're going to do that is factor it. No, actually, you don't have to be freaked out with it. I think some people may be a bit freaked out. There's a half here. How can I factor all that out? But really, keep the half in, keep the bracket in, then factor the 4 in the middle of the bracket before you take it out. So that's going to be 4 lots of 1 minus 9 over 4x, okay? Hopefully you can see that right. Let's do it step by step here. So I've not considered the half yet. I've just factored it inside the bracket to almost create two brackets. Okay, hopefully you see that step. Then I can factor it out by using this index law here. A to the mn is times in the powers together. But really, this is 4 to the power of 1. So this is saying 4 to the half then. And then this in the bracket, 1 minus 9 over 4x, is also raised to a half, right? Because it's almost like saying ab to the n is going to be a to the n, b to the n, where we have a product here. So the product here is 4, and this bracket here, 1 minus 9 over 4x. And all of that is raised to the power of a half for n. And so really, what this law is saying here, we can just split and we can distribute or spread out the power between the two products. And that's all we've done there. Okay, so actually, when you split this up, instead of trying to do it all in one go, to just factor the 4 out like this quickly, if you are struggling, you can do it step by step like this, and hopefully it should be a bit clearer. Okay, but then we can simplify this. 4 to the half is 2, right? Again, if you're unsure, use the calculator to check. That's our 2. Did I say half? I said 2. I meant to. I don't know why I said that. The halves everywhere. Anyway, 2, lots of this. 1 minus 9 over 4x to a half. Now, this is in this form here. Because now we could say, if I call this big X over n, then big X is going to be minus 9 over 4x. Hopefully you can see that. If I substitute that in, I get this same bracket here. And I can call n as a half, which is this index here. Then if I substitute these two into here, this formula here, then I get my expansion, right? So I'm going to ignore the 2, then I'm going to apply the expansion to this bracket here, because then I could just times by 2 at the end. Anyway, so let's do that. So the first term is going to be 1. Then the second term is going to be nx. So plus n, remember n here is a half. And then x is going to be here. So this x part here, minus 9 over 4x. Okay, not x, but minus 9 over 4x. Okay, hopefully you can see that. Then we have the next term, which is going to be n of a half minus 1 over 1 times 2, which is 2. So this is a product, by the way, and times in n by n minus 1. Okay, and then x squared. But remember, x is minus 9 over 4x. So that's going to be that squared. And then I need those are 3 terms, but I need 4 terms. Okay, so that's 1, 2, 3 terms. I need a 4th. So I'm going to continue on with the pattern here. So then it's going to be n times n minus 1. Oh god. Yeah, see, it's starting to get slower now on my laptop. Half minus 1 and a half minus 2. Okay. And that's going to be 3 times 2 times 1. So that's going to be 6. And that's going to be x cubed. So it's going to be 9 over 4x all cubed. Okay, and that's your formula there. If you are unsure here, as well with exactly what I would go to, notice this is the generic term x to the r, but you're going to want x cubed, right? So clearly r is going to be 3. Then you basically just substitute r is 3. So that's going to be n, for example, the top bit, n minus 3 plus 1. So that's going to be n minus 2. So you times involve n to n minus 2, which is what we've got here, okay? Likewise on the bottom, r would be 3. So it's going to be 1 times 2 times 3, which is what we've got there. So if you are a bit unsure, if you need to go to higher powers, you can again just use the formula to spot what you need to do. But anyway, it's so slow now. And now we just simplify it all, right? You can use the calculator to do this, so it's going to be 2, if it lets me. 2, lots of 1, and then I'm going to simplify the first bit, so a half times minus 9 over 4 is going to be minus 9 over 8. So it's going to be plus, well, minus 9 over 8 x. So I'm dealing with all the coefficient parts. Then for the next x squared term, it's going to be a half times a half minus 1. But then it's also going to be times by minus 9 over 4 squared. Why? So this bit here, because, again, like I did previously before, just minus 9 over 4x squared, x all squared, sorry. I can, again, spread the power out. So minus 9 over 4 squared, x squared, okay? So then that's the coefficient part. And that minus 9 over 4 squared can then be multiplied by everything else on the left before it. Okay. So the half of half minus 1, then it's times by the minus 9 over 4 squared, divided by the 2. And so the coefficient for x squared is going to be minus 81 over 128 x squared. And then for x cubed, it's going to be then a half of a half minus 1 of a half minus 2. And then it's going to also be times by minus 9 over 4 to the cube, right? Power 3 over 6. And so the coefficient of that would be minus 729. We'll get rid of that. About 1024x cubed. And that's our expansion. So then we just times by 2 to then say it's 2 minus 9 over 4x. So just times everything by 2. Times by minus 81 over 128 times 2. Might that be minus 100, minus 81 over 64x squared minus 729 over 1024 times 2. That would be minus 729 over 512x cubed. And that's your expansion, right? So that's saying that the square root, well, the original, so the square root of, what was it, 4 minus 9x, which obviously was a half, no, it's 2. That's of 1 minus 9 over 4 x to the half. And that's going to be approximate to this. Because remember, this would go on forever, but those were the first 4 terms. But there are more terms, so this is just an approximation, okay? But yeah, cool. So then part B. So what's part B saying? Then it says a student uses this expansion of x is 1 over 9 to find an approximation for root 3. That's a fairly common thing, right? Again, to substitute it to get an approximation for something. Then it says using part A without doing any calculations, state whether the approximation would be overestimate or underestimate for root 3. Given a brief reason for the answer. So what's going on is I'm plugging this value of x in, but you shouldn't plug it in because it said do not do any calculations. So we just have to stare at answer essentially. Let's say, why has it moved? There we go. I don't know. But what's going on here is it's basically saying if we use this 4 terms, would it be an overestimate or an underestimate to the true answer for this, right? Because remember, we only got the first few terms, so it's just going to be an approximation of the true answer for this square root bit. So here, say this is root 3 for x is 1 over 9. If we plug in x 1 over 9 to the first 4 terms, that number it gives us is going to be an approximation, but is it going to be above or below the actual answer for root 3? Well, really, again, like I said, it said just use the answer to just look at it. So, what do I see really happening? So, because I said it's the first few terms, what would the next few terms look like? What would the other terms look like? Because obviously then that would be the actual answer if we added all the other terms. Well, I noticed we have 2, but then it's minus x, some lots of x, minus some lots of x squared, minus some lots of x cubed. So we're actually minusing some amount each time, aren't we? So that's going to be minus k lots of x4, then minus k2 lots of x5, so more constants, some multiple of x5, some multiple of x6. So we're subtracting each time, aren't we? Because we're always subtracting. And that trend would continue, right? And you can kind of see that so if you're not entirely convinced because of the fact. Notice again, if we have an even, notice, say, with times in n by n minus 1, n minus 2, that's going to be even, and then all of these are going to be not even. Sorry, that's going to be positive. Then all of these are going to be negative because the half minus 1 is negative, half minus 2 is negative. But if there's an even number of what's it called? If there are an even number of brackets here, so it's going to be positive then negative, positive then negative. It's going to be negative, right? For example, with the x squared term here of let's go up. Oh, for God's sake. Say we have 2 brackets here, so the even number of brackets of products. We've got a positive on the negative, so it will go to a negative. But when it's even, this is an even power of x. So that means if it's minus 9 over 4 squared, that's going to be a positive number because it's an even. Likewise, on the other side for odd, again, we're now going to have an odd number product. So this is going to be positive. Again, look at x cubed. This goes to a positive coefficient because 2 positive and 2 negatives, they give a positive. But this then would be an odd power of a negative, so it's going to be a negative as well. So overall, all the coefficients, what I'm saying is, that's the kind of rigorous way of looking at it. But all the coefficients are going to be negative, and without having to go into that, you can just immediately spot it, right? But I'm just again giving like the full explanation behind that. But it's all negative. And actually, that means any further terms are going to be negative as well. So that means actually our true answer would be smaller, right? Because it would include more negative terms. And obviously x is positive, so obviously whatever you plug in x will be positive. So negative times positive will be negative. So actually this will be an overestimate. So our approximation or our expansion, if you will be an overestimate. Because the expansion involves negative terms of x, right? So less terms means a less negative answer, right? Hence an overestimate. Okay. Hopefully that made sense, right? But that's sort of the thing you got to get at. Okay. I think that's it for this part. I did split this up into 2. actually, because the next part is here. To look at the other questions. I thought I was gonna do more than that actually, but I don't know. There's been a little bit of a calamity, especially what happened earlier, my laptop breaking down. Uh, but actually, I guess it's quite fitting because I don't have more time sadly now. But I can do this part two in the next session, right? Um, because this goes from like question 9 to like 16, I think. That I took, so it's based like a past paper essentially, which is quite fitting because it's all the paper topic questions that weren't in paper one, and I've made a whole paper worth of other topics. So this could resemble quite nicely paper two. I don't know. It'd be good practice anyway. But yeah, that's half of the questions done. We'll look at the other half next time. Hopefully, it goes a bit smoother. um, but yeah, but that'll be Monday, I believe. The next time, but then I'll be doing it on Wednesday for the night before, where I pick certain high priority questions, right, like I did last time. Which I hope was useful, by the way. For those who tuned in to that video or whatever. But I should be doing the same again. But yeah, so that's the first part of this done. We'll tackle these questions um, next time. I guess I'll show them, right? But if you want to be a bit, obviously see this question here. But if you want to see like, if you want to be like a bit like, what's it called? If you want to see the questions fresh next time, obviously look away. But I don't know if you want to practice beforehand, obviously, or whatever, and then you want to tune in and see me go over a particular problem. These are going to be the harder questions, by the way, because these are going to be like towards the end of the paper. So obviously the earlier questions are going to be mostly easier. So these are going to be harder next time. Obviously, again, to reflect the paper. But if you want to practice it, go ahead and then obviously tune in next time or whenever. Obviously, then do whatever you want with it. Then go ahead. Uh, but yeah, I'm gonna leave that there then after this. So I'll try and publish this onto YouTube again. I'm gonna try and combine it because at the moment I've got two different streams because of the fact my laptop crashed. So I'll try and find a way to combine it so it's not disruptive. I don't want to split it up into two. Parts today anyway. But this will be a two-parter anyway, as I said. I'm going to stop waffling now, so I'm going to leave that there. But yeah, I'll see you next time. I'm going to do the next part of this, okay? Uh, but yeah, see you next time. Uh, um, hi, hello. So this is going to be a revision stream for paper two for A level, particularly with Edexcel. This will be part two of the session I did on Thursday, I believe. And I did the first 8 questions on this. But I didn't have a lot of time, so I had to leave it there. So, but this will be part two for it. And again, these are all topic questions that do come up in paper one that obviously usually do. So, this would be a useful resource, right, to help you prepare for paper two. So it's a good idea to make sure you have a good sense and a good idea how you would tackle these sort of questions. Um, but yeah, I am gonna just jump right in. Okay. Okay, so this question then, question 9. Trig modelling, which is very, very, very common to have a question like this. So firstly, so without even doing any modelling, looking at any information, we need to express this in this form, r cos theta plus alpha. And this is very common as well. So what this is saying is, well, 2 cos theta minus sine theta has to be in the form So identical to r cos theta add alpha. Um, why is this not loading? There we go. Okay. So we need to express it in this form. Well, the strategy of this is you're gonna like with pretty much anything with trig, you're gonna want to expand the brackets, if you will. So you're gonna need to use the addition formula for cos theta add alpha. And actually, I've done it here. So a plus b is this from the formula book. Therefore, cos of theta add alpha, if we substitute a for theta and b for alpha, that's going to be cos theta cos alpha minus sine theta sine alpha. Bearing in mind that is a negative because the negative is on top here, notice, but here it's the plus on top. So if we plus in, then we do need to take the top sign, so it'd be a negative. Okay, let's just be aware of that if we're using the formula book. And that's our expression, right? So we can therefore say, well, it's r cos theta of alpha, so we're going to times it all by r. So it's going to be r cos theta cos alpha minus r sine theta sine alpha. Okay, and now we should look, it looks pretty similar to this, right? And actually we can sort of compare coefficients. So notice I have a cos theta on this side and then a sine theta. So that means, well, if this has cos theta, that means we have to have a coefficient of 2. So that means, oh, r cos alpha has to be 2, right? If we just compare, you call that equation 1. And similarly, minus sine theta, well, that's going to be minus r sine alpha, right, to give a coefficient of minus 1. So therefore, well, minus r sine alpha is equal to minus 1. But I can just divide through by negative, right? So then I could just say r sine alpha is 1. And that'd be the second equation. Cool. And now we need to essentially find r and alpha, which we can do because we obviously have two different equations. And the trick with this is actually, first of all, you can square both equations, right? What will that give us? Well, it's going to be r squared cos squared alpha and r squared sine squared alpha, and that'll be 4 add 1, right? Because 2 squared add 1 squared will get us 5. Okay, cool. Now I notice I can factor an r squared out. So that'd be cos squared alpha add sine squared alpha, and that's 5. But then what do I notice about this? Well, this simplifies to 1, doesn't it? Because of this Pythagorean trig identity, cos squared theta add sine squared theta is always 1. So that means, therefore, that simply r squared is 5. So r is root 5. Not plus or minus, because r we pretty much always take to be positive. And it says it here as well, r has to be greater than 0. So r is root 5. Okay. And then, okay, so we found r. So how are we going to find alpha? And really, it's not. We could then just substitute root 5 into any other equation, and then, like, say for example, equation 1, root 5 cos alpha is 2. Then you can just inverse cos it and then get this solution alpha and pi over 2. But what you can instead notice, well, what if we do 2 divided by 1? Well, that's going to be r sine alpha over r cos alpha, which is going to be a half, 1 over 2. And why do I do it that way? I notice if I divide sine by cos, I get tan, because of, again, this identity. Tan is sine over cos. And the r's cancel as well, so therefore you're left with tan alpha is a half, right? Um, okay. That's slightly easier to solve. That's one way you can approach it. Therefore, alpha is going to be what? Then you're going to inverse tan it. And that's going to get you 0.463647 radians. Okay, but do we need to round it? Yes, we do. 3 decimal places. So that will go to 0.464, because the 6 will round the 3 up to 3 dp. But now we found our r and our alpha. So therefore, the original expression 2 cos theta minus sine theta. Remember then, we said that's r cos theta at alpha. So r is root 5, and that because of theta add alpha, wasn't it? Yeah, theta add alpha, which is 0.464, and that's our answer. Okay, so remember, we said it had to be in this form: r cos theta at alpha. R was root 5 and alpha was 0.464. That's what it worked out. You do not have to go for this whole step. I broke it down like this to show clearly where the r and the alpha comes from. But actually, if you're really quick and you're used to this, you should immediately recognize that r is going to be the root of the squares of the coefficients. So it's going to be 2 squared add minus 1 squared. That would get you root 5. And alpha will come from, well, you're solving tan alpha. You're dividing this bit by this bit, so minus sine theta. Oh, well, it'd be alpha over 2 cos alpha. No, so sine alpha over cos alpha, so tan alpha would be the minus 1 over 2. No, it'd be half, wouldn't it? Because we've got a half down here. Cool. And then if you solve for that, then you get alpha is 0.464. And then you can do it without this whole step. But if you ever are a bit stuck, exactly, then you can go for this sort of approach to get your answer. Okay, cool. So that's part A. That should be fairly straightforward. That's harmonic identity. Okay, so what's it saying now? Now we get to the actual model, right? Let's get rid of this. Cool. So we're given this little Ferris wheel looking thing, a water wheel, because it's in water. And it says begins some waffly stuff, right? I'm not going to read through it all. I'm going to highlight any numbers, but we're not giving any numbers. So the only thing I notice is h in vertical height. And where's t for time in seconds? And this formula here. Those are the only things that stare out to me at this point in time. Everything else just looks like waffle. So let's see what we can get from it. So then using the model, find the maximum height of P. So P is the maximum height is the vertical height in H above the water level. So the water level is kind of well, it's going to be like the ground level, isn't it? Here, look, the water level is sort of the ground level because H starts here as it shows us, and it goes up. It can go down as well, but then it'd be negative. But that looks like our initial level, right? It's going to be when H is 0. That's sort of our ground level, right? But yeah, so H represents the height of P, right? P is like this little wheel here. We want the maximum height, but the maximum height is going to correspond to the maximum of this value, isn't it? So if I write down this formula we're given, H is, what was it? 3 add 4 cos of a half t minus 2 sine of a half t. We want the maximum of this, right? But there are two ways you can do this, right? You can either differentiate and then do the normal process of setting a turning point to be 0, finding that is a maximum, and then going from there. But with these sort of questions, especially if only 3 marks, you really need to realise that actually we can just use what we know about the trig functions and actually part A, because they always ask us to do part A like this for a reason. And I noticed we can actually substitute this expression 2 cos theta minus sine theta in, because isn't this um, 2 cos theta minus sine theta? Then that's 4 cos of a half t minus 2 sine of a half t. Wow, that's going to be 2 lots of uh, root 5 cos of a half. Well, theta is going to be a half t, right? Because that's the angle we've got here, half t. So if I substitute this theta in, so then that's going to be half t, add 0.464, right? So therefore we can say this with, well, the 3, we add the 3 on, 3 add, and then I notice this is 2 lots of 2 cos theta minus sine theta, where theta is a half t. And then I could just substitute this in, okay? And that's the key thing, right? To notice you can compare and use what we've got. So then that'd be 2 lots of root 5 cos, so that'd be 2 root 5 of cos of a half t add 0.464. Cool. And now this is a lot easier to work with, because to actually see where the maximum will be, because we only have a single trig function, so we can kind of look at the graph, right? Which maybe will look something like this. To kind of deduce where the turning point will be, or the maximum value, because before obviously we had 2 different functions, 2 different variables, if you will, so it's quite hard to see because they'll conflict each other, right? But here we only have one variable bit. Like with completing the square, say if you had x, I don't know, minus 4 squared add 9, I can clearly see where the turning point would be. But then if I had x squared minus 8x plus 25, um, that's a bit harder to see just by inspection where the maximum and the minimum will be. But here, because there's fact there's 2 parts of x, right? But here x is on its own, so it's a lot easier to see. Anyway, because now we only have one trig function, one t involved. There's only one variable, instead of like 2 different variable parts, with the cos and the sine. It's easier to see, and actually you should realise that cos of any angle whatsoever, even if an angle looks like this, where like it's not just theta or t, it's a half t add 0.464. Any angle whatsoever, because remember, if we're changing the input of any function, that's not changing the y value. That's not changing the output, right? The range. That will always be bounded between 1 and -1, right? Right. Think about a normal cos graph. It's going to go 1 and -1. So you need to realise that as well, because that'll make your life a lot easier with these sort of questions. Okay, so with that in mind, the max, so H max then is going to be when cos of a half t add 0.464 equals 1, right? To get the most positive, the biggest value, right? So therefore H max is going to be 3 add 2 root 5 lots of 1. Right, that's just 2 root 5. Okay, cool. I'll be back probably in maybe a few minutes. I've got to do something. But have a look then. How would you work at the t value that gives the maximum? Okay. maximum height does occur, it's going to be when, like I said, this cos thing is going to be equal to 1. So we just simply solve it, right? So, for part 2 now, cos of a half of t at 0.464 equals 1. Well, firstly, we solve this, so you're going to do the arc cos, right? So then a half t add 0.464. That's going to be the inverse of 1, which obviously is 0, right? Obviously, you can just even look at the graph. So it's going to be 0 when it's 1. But then, obviously, let's consider some other solution. Let's consider the next one. Well, the next one's obviously going to be 2 pi, right? Because that's when the next one would be. So this would be 2 pi, that's 0. And so let's consider that. So then, therefore, t, I'm sorry. Oh, apologies. Pretty rough today. Anyway, I'm going to break this down, but you could just then rearrange for t, right? Because obviously we're solving for t, not half t at 0.464. But then I'm going to say, well, this t looks like a plus, doesn't it? Okay, I make it the t more curly. Therefore, half t, we're going to rearrange for t. Right, we're going to subtract 0.464, right? So it could be 0.464, then 2 pi and minus 0.464. So therefore, t, then if we just double, so therefore t is going to be 2 lots of 0.464, 2 lots of 2 pi minus 0.464. Okay. I didn't put it into calculator just yet because I wanna I don't wanna mess with rounding errors. You know what I mean? But actually, if we then put that into a calculator, that's gonna get minus 0.928, and then that will be 2 lots of 2 pi minus 0.464 will get us 11.63837, so on. But it's asking for the first time the height is reaches the maximum height, right? The first time. But time is time, so time has to be less greater than 0, has to be positive. So this actually, if we then just took the first value from the calculator, which is called the principal value, but the first value in the calculator will just get a negative value, so that cannot be a solution. So the first positive solution, which should be the first time which is 0, is actually their big T. No, you could call it big T, but I think it's just T. It's going to be 11.638 something, right? And that would be in, what's the units? In seconds, okay. And it asked us to round in it. What did it ask us to round to 1 decimal place. So that's going to be 11.621 dp. Okay, cool. So hopefully that made sense. You just got to be pretty careful here with what solution you take. And the best way is to, do the first 3 values instead of just the first one. Because like I said here, the first one actually wouldn't make sense because it'd be a negative time. We would want the first positive solution, which would be the next solution. Okay, cool. Part C. What? Okay. Um, then it says in a single revolution of the wheel, P is below the water level for total T seconds. Find, according to the model, the value of T. So what's going on here? Well, again, what is our equation look like? This H here. Uh, it's basically a cos graph, isn't it? It's going to look a bit like this or something like that, right? And you can see that here. If you look at the model, see it can go below the water level, right? So it would be underwater. that's corresponding. Well, what would that correspond to in this cos graph for h? So say this is h, and obviously that would be t. Just a general sketch of a cos graph, right? I don't care about the specifics, um, but just yeah, anyway. But it would be below 0, right? Here, right? Um, and that would correspond to where it's underwater. So therefore, the total time it is below water is going to be the difference of these two values, right? When it hits the water and then when it leaves the water. Well, that's going to correspond to the first two solutions to h is equal to 0, no? First two solutions for t. And hopefully you can see that the difference of the two solutions then would give us the time it's underwater, right? And that's what we're going to do then. So then h is 0. That's what we're going to solve, right? So we need to consider the values for t. So therefore, when h is 3 plus 2 root 5 cos blah blah blah. So that means 3 plus 2 root 5 cos of half t add 0.464, right? Equals 0. Uh, yes. Okay, now we need to solve for t. So let's just rearrange. So cos of a half t add, not, I did say I was going to make it curly, didn't I? Not that curly. T add, there we go. Half t add 0.464. That's going to be equal to, so the 3 would go to -3. And we'd then divide by the coefficient 2 root 5. Okay, you don't need to rationalize it, because we don't really need it particularly in a certain form. We just need to solve it, right? But then, okay, so this means we have to solve this equation, right? So then this particular scenario, again, sketch a general cos graph. -3, it's going to be something here, like it's going to be a negative y value, all right? So therefore, the solution is going to be here and here, right? Two different solutions. But let's just see this. So let's firstly, so then half t at 0.464. So if you do the inverse cos of that, that's going to give us 2.3061178. I'm going to keep the decimal points for now. Cool. Okay, but then we need another solution, don't we? Let's go to the next one. It's going to be here. How are we going to solve this? Well, the best thing to notice is the symmetry, right? If you're going to solve by the graph, it's symmetrical about this turning point, right? Which is at pi. So therefore, the difference between our first solution here and pi is going to be the same as the difference between pi and the second solution. Therefore, then the second solution, we can say, okay, well, pi minus our answer is our first answer is what? So it's going to be pi minus 2.306, blah, 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 is this 0.83. So that's our difference here between pi and one of the solutions. So because it's symmetrical, therefore we can add 0.835 to pi to get the next solution. Okay. That solution then, if I get rid of this now, that's going to be 3.977074528. Okay. So we only need two solutions, right? Because then we can find the difference to get the time. Okay, so we really effectively want the difference between these two solutions, but we need it for t, not for half t at 0.464. So again, we're going to need to rearrange both. So that means a half t is going to be subtracting 0.464 to both sides. So it's The second one, because we've already got that by calculator, it's going to be 3.513074528. And hang on, I'm going to make sure I wrote it down properly. 3.513074528. Okay, cool. I just doubt myself there. And then the first one, 2.3061178 minus 0.464. It will give me 1.842111078. Cool. So therefore, t are two values for the original equation when h is 0. So for t now, we then double it. So then t would be 3.684222156, and then double the second one, 3.513074528 times 2 will get me 7.026149.056, so on. Okay, so that's our two solutions. So then we need to take the difference, right? So therefore, big T is going to be, well, again, it corresponds to when it's underwater. So it's going to be, remember our sketch here. T is underwater for all this point. So it's going to be our second solution. So that's going to be T, remember, the difference when it's in water. It's going to be the difference between the second solution when H is 0 and the first solution. So therefore, big T is 7.02614, blah, 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 minus 3.6842, blah, blah, blah. And then that will get me 3.3419 something, and that would be seconds, right? Does it ask me to round it to something? Let me check. Three significant figures. Okay, so that will go to. I'm going to do it here. 3.34 to set s seconds to 366. Cool. So that's part two. It's probably the hardest part of the question. But I hope they made sense, right? So the big key part with this is to just understand and be able to use your cos and these sine graphs to help you interpret what's going on. But yeah, okay. Then it says at the end, in reality, the water level may not be of constant height. Explain how the equation can be modelled to take that into account. Refined. So this is the water level. So it's saying that might not be constant. So really, obviously, we're saying it's flat at the moment, but it could be like a wave, right? Which I guess would make sense, right? So how would we take that into account? Well, really, so we have to look at our equation then. This h bit here. Oh, here. Okay. Well, the water level is essentially like a y value, isn't it? When y is 0 or h is 0. Okay. So if we wanted to keep shifting it up or down, that's going to affect the sort of y value, I guess. But it's going to be a fixed number, right? So it's going to correspond to the constant, right? That we add after everything else. So if we want the water level to vary to stop being a constant, we need the free to vary, don't we? So therefore, to model it, to take that into account, I'll write that here, part D. We need to essentially to add another variable function of x, right? Or vary the free term in the function. Uh, um, because obviously if you're adding 3 to a cos graph, right, to any graph whatsoever, you're just essentially shifting it. upwards or downwards, and that will correspond to shifting the water level up and down. So we want the water level to keep changing. We need to add, a, we need to make the constant change. So we need to make it a variable. Okay, cool. So that's that sort of question. I think that's probably one of the harder modelling questions for trig. So if you get your head around that, then I think you'll be in a good position. Okay, question 10. Another trig question, actually, mixed with geometric theories. Okay. So we're given three terms of a geometric series. And we need to show this equation. Again, this is very common when you're given three terms of a geometric series and you need to show something. Well, the strategy is really to work to be able to understand what each term represents. So here, if it's a geometric series, this is going to be A for common for the first term. Then this is going to be AR for the R, the common ratio, and this will be AR squared, right? The first three terms. Well, if we stare at it, well, we could say, well, firstly, AR divided by A, so the first term divided by the second term divided by the first. Well, that's going to be R, but that's also going to be then 5 plus 2 sine theta over 12 cos theta. Likewise, then, we could divide the third by the second term to get AL squared over AR. That's just going to be R again, right? And that would be then 6 tan theta. The third divided by the second, and that would be 5 plus 2 sine theta. Cool. But now both of these are R, so they both have to be equal to each other. So therefore, 5 plus 2 sine theta over 12 cos theta, that's going to equal 6 tan theta over 5 plus 2 sine theta. Okay. And then here, then we just kind of simplify it to get rid of so we need to get rid of a fraction, right? So we're going to need to cross multiply. So therefore, well, 5 plus 2 sine theta is getting multiplied by itself, right? If we cross multiply here and here, right? So that'll just be squared. Put equals to, and then it's going to be 12 cos theta times by 6 tan theta. So therefore, and then we're going to need to expand this, right? Because there's no brackets in this form, so we're going to need to expand it, and that's generally the right thing to do. So expand it, so that's going to be 4 sine squared theta. Again, if you're unsure, literally write it out, because obviously squared means it's the same bracket twice times by itself. There you can do your normal method of FOIL or whatever, but really, hopefully you're quite proficient with expanding by now. But then I could just spot where it's going to be 4 sine squared. 2 times 10, 2 sine theta times 5 would be 10. Another term that'd be 20 sine theta. Add 25, 5 squared. So then that would be 12 times 6, which would be 72. Cos theta, tan theta. Okay, well, I noticed only sine terms. We have a sine squared, a sine, and a constant. But there's no cos or tan. So maybe I need to think, wow, tan, then I realise is going to be sine over cos, right? Because really I want sine, so I'm going to need to get tan in terms of sine, right? And actually, therefore, this will equal 72 cos theta times by sine theta over cos theta. Well, that will cancel, so we're left with simply 72 sine theta, right? Okay, now I can rearrange. So then I can say 4 sine squared of theta plus 20 minus 72 sine theta. It's going to be minus 20 minus 72 will get me minus 52 sine theta. And then add 25 equals 0. And that's what we've got up there. Lovely. Cool. Okay, part B. I'll do down here as well. Okay, part B. Now it says, given that theta is an obtuse angle measured in radians, we need to solve the equation to find the exact value of theta. Okay, so first of all, obviously we're going to need a domain, a range of values for theta. Well, actually, it told us it's obtuse. That means theta is going to have to be between 90. But it's in pi, right? It's in radians, right? So 90 to theta 280 degrees, right? But that will be in radians. So 180 pi and 90 would be pi over 2. So that is where we're working in. That's the values we need to work for theta. So we need to solve this equation, and you should recognise you should be fairly. This shouldn't be too unfamiliar if you practice your trig, but it's a hidden quadratic, right? And so say if I had said u is sine theta then, to help you visualize it, therefore 4u squared minus 52u plus 25 equals 0. And that's that I could spot how to solve that clearly now, right? But obviously if you are more proficient, then you can just jump right to solving, without any u's or anything like that. But if you're a bit shaky on it, then don't be afraid, make it simpler for you, break it down like this. But anyway, so then you again, I'm not sure that Mark scheme might be funny. They might say, well, you're going to need to explicitly show you solve it rather than using a calculator. Even though every calculator for A level should have the capability to solve quadratic, so it is expected you can just do it on your calculator. But if you want to be really cover your back, just write down the quadratic formula. It'll take seconds, right? So that'll be 52 plus or minus the square root of minus 52 squared minus 25 over 2 times 4. And then I put it into on the calculator solver. Don't then write this whole formula out. It will take ages. You can just then use the quadratic formula, but it looks like you then show your method, right? But you can just put it into the solver in your calculator. So then 4 is minus 52 and 25 will get me u is 12.5 and u is a half. Okay. Okay, so therefore that's saying then I plug u back in. That sine theta is 12.5 or sine theta is a half. Now one of these we're going to reject and hopefully spot which one. It's going to be this one, right? Because you need, again, like we did what's about earlier in the last question, you need to consider the range for sine. So remember the sine graph is between 1 and minus 1. You could alternatively try to solve it, and then you probably get like the calculator be like say math error, so then it can't be solved, right? But this is the reason why. Sine between 1 and minus 1, but clearly so sine theta is less than 1 or equal to 1. So sine theta uh, cannot be 12.5. Therefore, sine theta equals a half only, right? And that's what we solve. Now, we need to solve it between pi over 2 and pi, as we discussed, because it's obtuse. So to solve this again, you can use the graph to help you. So sine graph is going to look like this. So a half is going to be here. Actually, it's a bit clearer. There we go. So a half is going to look like here, and then it's also going to intersect here. So therefore, theta, if I solve, do inverse sine of a half, it's going to be pi over 6. But then that's not that is acute. That's not less than pi over 2 or 90 degrees, right? Because pi over 2 is the hump here. That's before the hump. We're then going to need this solution, aren't we? So then the next solution, again, look at the symmetry. Well, actually, this is not the most representative graph because 30 degrees, remember, is going to be like closer towards 0, isn't it? So it's going to be here, and therefore the next one's going to be here. So actually, you notice the distance between 0 and the first solution is going to be the same distance between pi, which is when this goes back to 0, and the second solution. Therefore, by the distance between 0 and the first root, which is pi over 6, is just pi over 6, right? 0, pi over 6 minus 0 is still pi over 6. So therefore, this next solution comes from pi take away pi over 6, okay? Because it's the same distance by looking at the symmetry around the hump, right? That's the key thing with solving these trig equations, is to notice the symmetry around the hump, or whatever you call it, you know. So therefore, then pi minus pi over 6 will get to the next one. Well, that's just 5 pi over 6. Okay. Uh, Theta is obtuse. Therefore, theta has to be 5 pi over 6. That's the only obtuse angle solution here. Okay, so that's our answer. Cool. Then part C says, show that the sum to infinity can be expressed in this form. So it's a geometric series. So we know now that theta is 5 pi over 6. But I said, I copied down the geometric series formula in the formula book. Sum to infinity is here, right? This is the sum to the first n terms, but we want to go to infinity. So that is going to be this one here. It says S infinity here, if you can see. That's what you're going to want to use. But we need that A and R, don't we? We need a common ratio. But we don't have any. We just have it in terms of sine and cos or whatever. We want an explicit number. But now we know theta, we can just substitute it in. Therefore, A, first of all, is our first term. Remember, go back. A is 12 cos theta. So that's going to be 12 cos of 5 pi over 6. And that's going to get us minus 6 root 3. Okay, then R, well, R, we kind of worked out pi, didn't we? R was any of these two terms. So R then, for example, then the common ratio is going to be, for example, let's do this one, right? Because this one I can see on the screen. 6 tan theta, so theta is 5 over 6. And that's over 5 plus 2 sine of 5 over 6. Cool. Then let's just put that into the calculator. And that will be minus root 3 over 3. Cool. So now we've got all our ingredients right to then get this formula for the infinity. So therefore, the sum to infinity by the formula, which is in the formula book. So that's going to be A, which is minus 6 root 3 over 1 minus R. So it's going to be 1, well, minus of minus is a positive, so it's going to be just 1 plus root 3 over 3. Okay, now we need to simplify this, right, to get it to look like this. So let's just simplify this. So the first thing, may it might be a little bit tricky to see what to rationalise, perhaps, because you've got this weird fraction in a fraction. So the best thing, firstly, is to just simplify this bit, right, to get as one whole fraction. So that's going to be uh, minus 6 root 3. And then put this as a fraction. Well, this is over 3. So this is going to be 3 add root 3 over 3. Now, actually, when we then divide like this is same as times it by 3. So this would be my 18 on top, and then we can get rid of this. If you were unsure about stuff like this, minus 6 root 3 over 3 add, what was it? 3 add root 3 over 3, was it? Recognise this is a division, so then we can say that's minus 6 root 3 divided by 3 plus root 3 over 3. Then you remember from GCSE, KFC, you keep flip change. So minus 6 root 3 you keep times, and then that will flip to 3 over 3 plus root 3. which is the same as times in 3 on the top, okay, which is where we get that. Okay, cool. And now this is a lot easier to recognise, to rationalise. We're going to times by its conjugate, aren't we? So therefore, we're going to times by 3 minus root 3 over 3 minus root 3. This will give us a difference of two squares. So that would give us, well, minus 18 root 3 times by 3 minus root 3. All over, well, that would be 9 minus 3, because the difference of two squares, so you have 3 squared minus root 3 squared. It's going to be 9 minus 3, okay? Again, if you're not sure, you could just, do the full, like, expansion, right? To see that it does simplify to 9 minus 3. And actually, this then simplifies to 6, doesn't it? 9 minus 3. So we just need to deal with the top part. So then, that's going to be minus 8. Well, we're going to times by 3 first, aren't we? So 18 times 3 is 54. So it's going to be minus 54 root 3. And then we're going to be times it by minus root 3. So it's going to be plus. And then 18 times root 3 of root 3. That's with root 3 squared, which is 3. Okay, and then that would go to 54, isn't it? Cool, and that's all over 6. Well, actually, then 54 divide div 6 is the multiple 54, so 54 is divisible by 6. So we can simplify it to then minus 9 root 3 add 9. And that would then simplified, factorise then to 9 of 1 minus root 3. And actually, is that our answer? Yes, it's in this form here, k of 1 minus root 3, where k is 9, right, as you can see here. And there we go. Cool. Okay. Another to mention, this was actually in paper 2 in June 2022. It seems to really love copying, as you see for paper 1, the 2022 exam series. So this is a good question perhaps to get your head around. They might ask a very similar one, so just be prepared. But yeah, that's that question. Cool. Question 11 now. So we are given a curve C with parametric equations. X is t squared of 6t and y 6 ln t of 3. Show that a Cartesian equation for C is this. Okay. So this is very common. You need to get y and x together from a parametric. Okay. So there's two strategies to this. The first one, you could say, well, y is a ln, well, x, you can just substitute of t squared at 6t minus 16, add b. But that doesn't explicitly help us, because then we'd need to say, well, and then we could simplify to get to 6 ln. But it's a bit tricky at the moment. So we probably, so if you can't just directly substitute like this, then you're going to need to consider kind of getting t on both sides in a way. So we kind of need, well, y is going to be really tricky as well, because it's going to get some, well, we need y, don't we? So it's not going to be y, so substitute y into x, because here we're substituting x into y. So actually we kind of need to get some t in the form of f of x, right? Rearrange, which then I can kind of sub into y. Because substituting in x directly, as we saw, is a bit complicated. It's not really clear what to do. So, okay, so we have x is t squared at 16 minus 16. Like I said before, we need t on its own to rearrange for x. Well, actually, how would we rearrange? Is a quadratic? Well, I know how to make a quadratic go to just one term of t. That's completing the square, isn't it? So we can then say t had 3 squared minus 9 minus 16, which is complete square form, which goes to t had 3 squared minus 25. And therefore, to get t on its own, t plus 3 squared is going to be x at 25, by moving 25. Therefore, t at 3 is plus or minus the root of x plus 25. Okay, but we have this plus or minus here, but we are not solving exactly. We're not finding a particular value. We're just finding a general expression. So when you're just rearranging stuff, if you're not solving directly, you can just get rid of the plus or minus and just add the root in. Okay. Um, okay. So t plus 3 is this. Now you could say t then is then minus 3 add root x plus 25. But actually we don't need to, because actually t plus 3 is already in y. So it doesn't make any difference really, but it just makes it a teensy bit easier to work with. Well, therefore, now we've got t, so therefore y would be 6 ln t at 3, which is going to be 6 ln root x plus 25, okay? But I know how to factorise this. Well, not factorise it. I can simplify this log to get just x without a third in. And that's going to be this rule here where uh, root x is x to a half, right? So it's going to be 6 ln of x plus 25 to the half, okay? And then I can use the log law where if I have a power inside, I can bring it out to n ln x, okay, or n log x. So that's going to be 6 over 2, 6 times a half, which will go to 3, ln x plus 25. And actually, that's now in this form, isn't it? So we've shown it. So therefore, a is 3 and b is 25. But you don't have to write that, okay? But that's just showing you directly, explicitly, that we got it in the form. Course, that's probably the trickiest part, I'd imagine, to spot immediately originally what to do. Like I said, usually you could just try and substitute x in directly, and then eventually you can kind of get y. But it's tricky because first of all, we have this complicated expression for t, so and it doesn't really go to this form, really. I don't know. Um, but also there's unknowns as well. So actually, you're not really verifying. You kind of, in a way, solving to find A and B. So you don't just really directly sub it in. So in that case, again, instead, you're gonna have to try and get t in terms of x, and then go from there. And then substitute the t in for y here, and then you get to this form. So that's generally how to spot what to do. But in other questions, particularly when you have like trig and stuff, when it gives you, for example, I saw, for example, like I think it's like 3 add a half of x minus 2 squared or something like that. When you're given like two parametrics, there you can probably sub x in directly because we've got actual values to work with, and it simplifies quite nicely. But if it doesn't simplify nicely, then you try. I do say do not really ever try and sub t in and inverse it and stuff like that to get t. But in this case, it's the best thing to do because everything else fails, or doesn't work nearly as nicely. So in that case, then I rearrange to get t and then substitute it into y, and it works nicely. Okay, so that's part A. Part B. Then it says the curve C, which again is equivalent to this, cuts the y-axis at the point B. Show that the equation of the tangent to C at point at P can be written in this form. So tangent's key. So that means we're going to need to differentiate to get a gradient. So the first bit is, well, dy dx then, because we're going to need a tangent, so we need a gradient. Well, y is now 3 ln x plus 25, which we've shown here in part A. So to differentiate it, well, you could use the chain rule, so u is x plus 25, but you should be able to do it quite, in one step, in one go. So it's going to be 3 because it's a factor multiplier. So 3, and then we do differentiate ln x plus 25. Well, ln of anything goes to 1 over, well, it was x plus 25. Then we times by the derivative inside. Well, x plus 25 just goes to 1 because 25 goes away because it's constant, and x just differentiates to 1. So times by 1, wow, it's just itself really. So that's the function. Okay, now that's a general gradient. Now we need it at P, but we are told that P is on the y-axis here, somewhere here. So that's going to be when x is going to be 0, right? So it's going to be 0, y. Well, how can we find y? Well, we already know what y is in terms of x. So therefore y is going to be 3 ln 0 at 25. That's just going to be 25. And I guess we leave it in this form, right? Because it's not asking us to round, so we need the exact form. So therefore, p is going to be 0, 3 ln 25. So therefore, dy dx at p is going to be 3 add 0 for x at 25. That'd be 3 over 25. And that's your gradient of the tangent. So then the tangent equation, well, it's a general line, right? So y is mx plus c. There are other forms you can use for the line, but I think this is it doesn't matter. You still need the same information for all of them. So objectively, one isn't superior to another, but I don't know. I think this helps you see what's going on. I don't know. But obviously you could use y, for example. Y minus y1 is m. X minus x1. That's cool. But it doesn't really matter. Okay. But m, we just worked out at p, is this here, 3 over 25. So that means that y then, the equation of the tangent, is 3 over 25 x add c. Okay, now we need to find c, but we know a point, because p also lies on the tangent. So we're going to sub the point in. P is 0, 3 ln 25. So therefore we get 3 ln 25 is, well, 3 over 25 is 0, add c, so that's just going to be c. Therefore at the end, y is then 3 over 25x add 3 ln 25. Cool, so that's our equation now, right? But it's asked us then to rearrange it in this form, okay? Where a and b are all the coefficients are integers. Okay, so we need to kind of match it here. So I'm going to rewrite what it needs to look like. Ax plus by equals c ln 25, right? That's what we need to rearrange it to. So first of all, let's just get the y and the x and y's on the same side. So it's going to be minus 3 over 25 x add y is going to be 3 ln 25 to kind of match this, right? The x and y's on the same side, the constant on the other. Now it needs to be an integer, a and b. So therefore, we get rid of the fraction. So we're going to times by 25 to get rid of the fraction. So therefore, minus 3x add 25y. It's going to be 3 times 25. That's going to be 75 ln 25. Okay, cool. Okay, but it's in ln. It says ln 5, not ln 25. So that means then that ln 25 has to be in the form of something ln 5. How are we going to do that? Well, 25, we're going to need to split into 5, aren't we? So 25 is going to go to ln, well, I know 25 is 5 times 5. Well, that's 5 squared. And so therefore that'd be 2 ln 5. So therefore this is now 75 and then ln 25 is 2 ln 5. So therefore, minus 3x add 25y is going to be 75 times 2. So it's going to be 150 ln 5. And now that is exactly in this form here, so we're good. And a is minus 3, b is 25, c is 150. They're all integers. So we're good. Cool. And that's it. So 4 marks. Great stuff. So expect differentiation like that to come up. But yeah, that's good. Okay, question 12. Okay, so I expect a sort of nasty sort of modulus question to come up. So it's good we go over a question like this. Okay, so we are given the number of subscribers of 2 different streams, and which are NA and N, which is given by the formula, and NB, which is given by this. So we're given all the numbers, right? But I pay attention to the units always with modelling questions. Pay attention to the units. Number of subscribers are in thousands, So I'm thinking we're going to need to times by 1,000 for any number we get. Okay, so I'm going to bear that in mind. Okay, but anyway, we've got all the formulas, right? We've got the graph. We can work with that without any pay attention to the wording. And T is time in years. Okay. So always pay attention to the units and the variables. Okay, underline it or do whatever you want. Just make sure you pay attention because sometimes, like with this, they throw you off guard and saying thousands. Because part A then is saying find the initial difference between the number of subscribers in company A and B. So that's just going to be NA minus NB at T0, right? That's the difference between A and B. Well, NA is mod T minus 3, but T0, so it's going to be 0 minus 3, mod 0 minus 3 at 4. Then minus NB is going to be this part here. So it's going to be something like that. B is going to be 8 minus mod of about 2t, that'll go to 0, so it's going to be minus 6. And that's our difference. So then that's going to be minus 3, but the modulus, the whole point is that it flips a negative to a positive, okay? So that means the negative version of the positive will give the same result, okay? That is the whole definition of the modulus, okay? So minus 3 would go to 3. And then add 4, then we add minus 8, then minus we add mod minus 6. Well, that will just go to positive 6, okay? And so therefore, we'll just compute this sum. So 3 add 4 minus 8 add 6 gets us 5. Okay, but it's not 5 subscribers, is it? Because it's in thousands, as we said. So this is going to be 5. So it's going to be 5,000 by times by 1,000 subscribers. Okay. So that is where you need to pay attention to modelling questions like this. Oh no, it requires genius brain. I mean, yeah, it does look tricky, doesn't it? But it doesn't have to be as bad as it looks. But yeah, so that's just part A, just using the model. Okay, let's read what it says after. When T is capital T, company A reduced its subscription prices and the number of subscribers increased. Suggest a value for T given a reason for your answer. So what's saying is company A reduced its subscription prices, so the number of subscribers increased. So really that's suggesting that it had a big dip and then it's going up again because that's when it reduces subscription. Well, where is it going down and then going back up? It's here, right? That's clearly where they started reducing the price to get more customers. But then how do we work out this? So this is going to be at capital T. How are we going to work this out? Well, what I notice is that this is where the line changes gradient, right? It changes, it's like 2 different lines. That's when they sort of intersect, right? This first line here and then this second line here. Okay. When that happens with a modulus, when they start to like bend like this and they change gradients, that is when the modulus part has to be 0. So remember, NA is mod t minus 3 add 4. The modulus has to be 0 for this bend to happen. Because remember, when, for example, we sketch a graph, say for any a straight line like this, say over here, the modulus version will go like this, but then it will bend upwards because we want to get out of the negative y-axis. So that's this bending that we're seeing here and here. But that bending happens when the x value hits 0. So in other words, when the y value hits 0, sorry, because it's on the x-axis. So that's when the modulus part has to hit 0, and that's when it starts to change course and change its gradient. And that's when it starts to bend or shoot upwards or whatever. So anyway, I know NA, so it'd be up here, wouldn't it? My apologies. So that's NA, so that would correspond to this point, right? At T. So we need to set this to 0 then. That's when it's clearly, no, no. What does it say? NA or NB? No, company A. Hang on, which one's company A, company B? Company A reduced its subscription price as the number of subscribers increased. Yeah, no, this is NA. Sorry, the label is really weird. Oh, this line's NB, and this line's NA. That's say. It wouldn't make sense for this to be because then it's going down. I don't know. Anyway, so that's the point. So then that happens at that value of t. This modulus part t minus 3, that part in NA has to be 0 for its line to change course like this. That always happens. Okay. So therefore, t occurs when t minus 3 equals 0. But therefore, that's going to be t3. Okay. And that's our select suggestion, right? And t, therefore, is going to be 3 years, right? Because t is times in years. Give a reason because that's when the graph wise NA starts increasing, right? Which means hence more NA gets more subscribers. Cool. So that hopefully that makes some sort of sense. But in general, whenever you have a bend like this, when it change course like this, with a modulus graph, that's when the modulus part has to be 0. Because then that's when the gradient changes. And like I said, that's when this bending, this reflection happens. Because that's the point where it goes from positive to a negative. So that occurs when the y bit is 0, so the modulus bit has to be 0. Okay, then part C is probably the tricky part. Find the range of values for t for which NA is greater than NB. Okay. Give me answer set notation. Okay, so we need to essentially find the values of t when that happens. So in other words, our graph NA, remember, is this one. So if NA is greater than NB, strictly greater than, that means the graph of NA has to be above NB. So it's going to be, well, NA is again this graph here. So it's going to be between here, right? Between 0 and say T1, and then up here, right? Where the intersection is T2. because then that's when NA is above this graph NB here. And that's the value of the t that happens. So then really we just need to find these values of t. So we need to find the intersection points here and here. But how are we going to do that? Well, let me get rid of this now to make the graph clear again. We need to find the intersection points. So we basically, there are two ways you can do this. Consider the graphical part, or you could do it an algebraic way. I'll show the graphical part, which I think is probably better for more questions. But so the intersection point, you need to consider, like I said in part just earlier about the modulus. You basically, the modulus is essentially two different parts. So for example, NA is mod t minus 3 add 4. That's going to be either t minus 3 add 4, but just making this bit positive, or minus lots of t minus 3 add 4. Those are two different graphs. But which one do we spot? Well, we can use the gradients, right, to tell which sign to take if we need to keep it positive or negative. So at this intersection point here, remember NA is this line here. NA is this line here. So the gradient is decreasing because NA is going downwards. So that means at this point, we need to take the bracket to be minus t minus 3 add 4, because then that would give minus t add 7. That would give a gradient of minus 1, which would be negative. Okay. So the key point here is to consider gradients to help you deduce if you need it, because obviously when you solve a modulus equation in general, say for mod x is like 6, something like that. Well, it's either x is 6 or minus x is 6. So you do plus or minus. You need to basically work out if you take plus or minus. That's what we're doing here. But here we have to have a minus because that would mean minus t, which should give a negative gradient because it's going downwards here. Okay. Likewise for NB, so we'll say at T1. For NB, this graph here is going upwards at this intersection. So that means if NB then is 8 minus 2t, we're going to need to do the minus of the bracket, right? So minus of minus 2t minus 6 to give us positive 2t minus 6. That would give us a positive gradient of 2. So it's showing it's going upwards, so it has a positive gradient. So that's what we need to solve, okay, to find the first point of intersection. So for T1, or the first point of intersection, so NA is going to be minus t minus 3 add 4. And so when we equal that to NB, the component of NB we want is the negative modulus part. So it's going to be 8 minus of minus 2t add 6. But that'll just go to positive, right? So it'd be 8 plus 2t minus 6. Okay? Because that's, and that's an add, not a t. So that'll give us a positive gradient for B and a negative gradient for A here. So that'd be minus t for A and 2t for B. As you can see again, once more to re-emphasize, A here is a negative gradient at this point, and B is positive. So we need to make sure we adjust our equation to match the gradient. Okay, let me just solve this then. So it's going to be minus t add 3 add 4, it's going to be minus t add 7, and that's going to be 8 add 2t minus 6. There we can rearrange to say 3t is going to be 7 minus 8 add 6, which goes to minus plus 5, right? So therefore t is 5 over 3. And that gives us our intersection point. Well, the t value anyway. So therefore t1, that's going to be 5 over 3. Now we need to do the same for this point here. So again, at this point, NA here, that's now a positive gradient. So we're just going to keep it as t minus 3 over 4. So we keep the modulus of positive as it is to give us a positive gradient of just 1. Okay. But for NB, down here, it's a negative gradient. So again, we're going to keep the modulus the way it is, because then it'd be minus 2t. So that it gives us a negative gradient. So therefore, we just take the modulus off to then say at t2, then t minus 3 add 4 will get us 8 minus 2t minus 6. And then that gives us t add 1 is 8 minus 2t add 6. So then I can solve again to say 3t is 8 plus 6 minus 1, so that'd be 13. Therefore, t would be 13 over 3. Cool. So that's our second intersection point. Here. So therefore, that is now going to be 13 over 3. Okay, now we've got our intersection points. Now, like we said at the start of this, to find the values when NA is above NB, so this line of NA is above NB up here. That's going to occur from here to the intersection point here, and from the intersection point to up here, right? So therefore, it's going to be between 0 and 5 over 3. And above 13 over 3. And that's our solution, right? So therefore, values of t are 0 between t and 5 over 3, or t is above 13 over 3. And I notice it's a strict inequality, so NA has to be strictly greater than NB. If it's at the intersection point, then they're equal to each other, so we need to be above the values of t here. Okay, strictly above. So those are our values, cool. But then it asks us to give an answer in set notation. So this is just something you need to know. So to give this a set notation, so we need to say, well, then the solution is equal to, well, this curly bracket to represent a set. And we're going to say t such that 0 is between t and 5 over 3. Or, I remember from GCSE, or even from the probability stats section of the course, say with Venn diagrams, if you want to say or, say we have two sets, A or B, that's we represent that by this U shape, isn't it? By U for union. That's what we're going to say here for set. So or is going to be this U, and it's then going to be another set, so another curly bracket of t, such that t is above 13 over 3. Okay, and that's what it did, and that's set notation. So this reads the value of values of t, and then the colon is such that. Okay. And then obviously you give your inequality there. But the key thing here is you only give one inequality, and then when you want to say or, then you have to split it to this U shape and then give two different brackets. These represent two different sets of values. So we need to split each inequality up like this by two different sets, okay? And that's set notation. But just remember, that's the general format, right? So t such that, and then give it inequality. And then if you have two or more inequalities, then you need to split that up with u, okay? As I've drawn here. Okay. So that's the bulk of that question done. Let me just see. Hopefully I did that right. I didn't make any errors. Let me check. Where's this question from? 2023, wasn't it? Do, 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 do. T such that t is less than 5/3, but obviously t is also greater than 0 because t is time, right? So t greater than 0 is an implied condition, or t is greater than yeah, cool. So I got that right. Cool. But then obviously there's a part D as well. Just a little one mark as usual with these modelling questions. State a limitation for the model used for company B. So that's very common. And probably one of the best ways of doing it really is to consider uh the limits of certain values. So company B, remember, is going to be, if we get rid of all this waffle now, um it's this shape here. This shape here. This line, this graph here. But actually, if we can then just continue this on, what would happen for large values of t? It's going to go negative, isn't it? Right? And you can see that here because eventually, when t gets large enough, this bracket will become, this modulus will become large as well. It will go to infinity. But we're minusing a larger number, so it would give us a negative value overall. So actually, this occurs. Um, it goes to 0 when well when y 0. So that means 8 minus 2. Hang on. So 8 minus mod 2t minus 6 equals 0, right? Therefore, mod 2t minus 6 has to equal 8. Um, uh, and that would mean then, well, 2t would equal 14. So t is equal to 7. So this occurs, so it hits 0 uh, if we continue it when t's 7. And that's saying, well, after 7, when t's 7 years, it's a negative value, right? That cannot happen. So when t is greater than 7, the model predicts a negative number of subscribers, right? Because that's what the NB is saying of subscribers, uh, which is nonsensical. Okay, so it's not realistic, uh, and so that's a limitation. Okay, and that's the general sort of thing you want to go to. You could say when t is greater than 7. I would check the mark scheme, but I think you could just say for large values of t, or when t goes to infinity, something like that. Let me check. It just says the number of subscribers would be negative. Okay, so you don't even have to specify what value of t is, as long as you comment on the fact it becomes negative, which is a general sort of theme in these sort of modeling questions. It gives an actually for limitation. It's a good idea to consider if it goes negative, and therefore that might be a problem. Okay, but cool. So that's that question done. I think there's two more to go for. Quite short questions actually, but tricky though. Let's read. It's so hard. You must be a genius. I would say it's just a lot of practice. I've done loads of maths over the years now. Not for a few years because I've not been in education for a while now, but I've still got it because the thing is with maths as well. I think people should how I still remember the maths now is because it all makes logical sense rather than just me memorizing stuff. I think when you actually start to remember maths, and start to know why it makes sense and why you do every step, why you do what you do, then it becomes logical and it becomes easy in a sense, as you build up more and more. So my strategy for that is obviously start from the basics to what you are most comfortable with, and then do some questions, but then in the answers, and this goes for A level as well, when you look at a mark scheme or a working out, go through line by line by line to every line and make sure you know exactly why that person or the mark scheme, the answer did that line. And then you go line by line till you get the answer. And then once you know why every line is done and why every line makes sense, you therefore know why you got the answer and why the answer, how you get to the answer. And that's how I did it. And now a lot of this sort of makes sense, right? Without trying to memorize certain stuff. Uh, but yeah, I'd say it just takes time and practice. But yeah. Okay, question 13. But I do thank you for the compliment there. But question 13 now. Again, this I think this is going to come up as well. A very sort of tricky, well, I mean, I think it's objectively quite tricky for A level anyway. A tricky differentiation question that will be with quotient rule. Expect a question like this to come up. So let's have a look at this. So the curve C has equation x squared tan y is 9. First of all, show that the first derivative is this. Okay, so firstly, I notice we have a implicit differentiation, an implicit equation, so we need implicit differentiation because y is not on its own. We have a tan y mixed in, so we're going to need implicit differentiation. Okay, so so we're going to differentiate with respect to x, but remember, really, there is an underlying function, y is f of x. So actually, y is also in terms of x. Y is also a function of x. So we're going to bear that in mind. But it's not really explicit because it's implicit. But that's generally what's going on, right, in the background. We could rearrange for y, but it's going to be quite nasty. But remember, y is in terms of x right in the background. Anyway, so we're going to differentiate this with respect to x. So why I bring this up is because it's going to be a product rule, isn't it? Because x squared is a function of x, but so is tan y, because tan y is going to be tan of another function of x. So they're both functions of x. So it's going to be a product rule. Y is again another part of x. So if you have an x and y together in an implicit equation, you're going to need the product rule. Okay. But anyway, so firstly, the product rule. You should remember this is not given in the formula, but we have two functions f of x, g of x. The derivative of that is going to be the derivative of one function with the keep the other the same. Then you differentiate the other one and keep the other function the same. So with that in mind, first we're going to differentiate the x squared, so that's going to be 2x, and then leave tan y as it is. Then we're going to keep x squared, and then we're going to differentiate tan y. So firstly, for tan y, you treat y, you differentiate tan of y like it's just x. So what is the derivative of tan x? And actually, I've copied the derivative section in the formula book. You actually don't need to know the derivative of tan x uh, by memory, but they might ask you to prove why the derivative of tan y is going to be sec squared, right? Because here we have f of x, which is tan of kx, and it gives us the derivative, which is f dash. And if then tan of y or tan x, well, k is 1. So that's telling you the derivative uh, of tan x is just going to be sec squared x, okay? If you just set k to 1, okay? So that means tan y will go to sec squared y. But when we differentiate any function of y in an implicit differentiation, every time we differentiate y, you then need to tag on a dy dx, okay? Um, And yeah, I won't explain that right now, but that's essentially the methodology. And then you differentiate 9, that's just a constant, so that'll go to 0. Okay, well then, I'm going to get rid of this now to make more room. Okay, well then if we do a derivative of implicit differentiation, the step you then do is rearrange, right? So dy dx then of sec x squared sec squared y. That's then going to be minus 2x tan y. Okay, hopefully you can see that. And then you just get dy dx. And that's then going to divide through, so minus 2x tan y over x squared sec squared y. Okay, but then I can do some cancellation immediately. The x will cancel, so it's minus 2 tan y over x sec squared y. Okay, but we need this form here, and I notice it's only x is involved, so I need to get rid of the y. Well, the only relationship I have between y and x is here. So therefore I can then say tan y is going to be 9 over x squared. That's helpful because I know tan y straight away. So I know that's going to be minus 2. Tan y is going to be 9 over x squared. Cool, so that's in terms of x. So an x. And then I'm going to need sec squared y. But I only know tan y. How can I then get tan y to sec squared? And hopefully you remember a certain formula or identity that links them, okay? And that's going to be 1 plus tan squared y is sec squared. That's how we link tan to sec, okay? But this is tan squared, but we are tan. Well, therefore tan squared, we can just square it, right? So it's going to be 9 squared is 81, and x squared is going to be 80x to the 4. So therefore, tan squared y, well, that's sec squared, right? So therefore, sec squared y is going to be 1 add tan squared. So it's going to be 1 add tan squared here. So it's going to be 1 add 81 over x to the 4. Okay, and now we just need to simplify this bit, right? So that's going to then be minus 2 times 9, which is minus 18 over x squared. That's going to be all over x, add 81 over x cubed, right? But then times x by the inside to the bracket. Okay, what do I do now? Like I did with the other question. Again, if I've got this weird like fraction and a fraction, just add them together first. So it's going to be minus 18 over x squared over, well, x over 1. I'm going to need the times by x cubed to get x to the 4 and 81 to get a common denominator of x cubed. Then I notice, well, x squared will cancel the cube to get just left with x. Like I said before, if you are really struggling to visualize what's going on here, recognize this is a division of minus 18 over x squared divided by x to the 4 and 81 over x cubed. Then you remember KFC, so you keep the first fraction, minus 18 over x squared. Then you change to the times and you flip to x cubed over x to the 4 and 81. Then that will go to minus 18x cubed over x squared x to the 4 and 81. Then then obviously the squared will cancel the cube. So left with minus 18x over x to the 4 and 81. So this then goes to minus 18x over x to the 4 and 81. And actually, isn't that what I wanted? Minus 18x over x. Yeah, there we go. Lovely. So like I said, if you've got a complicated division like this or fraction, don't be afraid. But you can break it down again just like this, right? And that would be x to the 4 and 81. Okay. And obviously notice we broke it down there. Okay, if you are struggling. But there we are. Lovely, lovely. So that's part A done. Cool. Again, that's probably going to come up right. I reckon a question like that will come up, like a tricky differentiation where you got like implicit, you got all these sort of trigs. You got a parametric in a way. I don't know. Expect. Hopefully you are comfortable with that question now that I went over it. I need to charge my laptop. There it is. Found the charger. Okay, cool. So that's part A. Then part B. Then it said, prove that C has a point of inflection at x is at the fourth root of 27. So point of inflection, firstly, that has to mean the second derivative is d squared y over dx squared has to equal 0, right? So we're going to need a second derivative, okay? So we have dy dx, remember, was minus 18x over x to the 4 at 81. We need to differentiate this again, but this is clearly a quotient rule, okay? But actually in the formula book, they give you how to differentiate the quotient rule here. So if we then say f of x is minus 18x and g of x is x to the forward 81, right? The numerator and the denominator function of x. Well, then we're going to need to compute the derivative of f dash and g dash, right? To then sub it into the quotient rule. So f dash of x is then minus 18, and g dash of x is going to be 4x cubed, and that's it, right? Because the 81 goes away because it's a constant. And then, yeah, and then we just use the quotient rule here. So therefore, d squared y over dx squared, if we then say f of x over g of x here, then the derivative is going to be f dash, which is going to be minus 18, of g of x up here. And g of x is x to the 4 add 81. And then we need to minus f of x, which is going to be minus of minus 18x, so that's just going to be positive 18x, of and then g dash of x, which is going to be 4x cubed. And then that's all over g of x squared, so that's going to be x to the 4 add 81 all squared. Okay, now we need, remember, we need a point of inflection, which occurs when d squared y over dx squared is 0, so that has to equal 0. Well, when a fraction like this is equal to 0, that means the numerator has to equal 0. So that's going to mean minus 18x of x to the 4 add 81 add 18x of 4x cubed has to equal 0. Again, if you were struggling, you might think, wow, you could just times the denominator by 0. But actually that just goes to 0, right? So then that just means the numerator is 0, and we get where we are here. Okay, but now we need to solve this. We need to find a value of x. It's very tricky to solve this, explicitly, but we're already given what the solution is. We want to show x is fourth root of 27. So really, we can just sub that in. Dark, can't we? And then if the second derivative is 0, that could be a point of inflection. That's one of the criteria we need. So let's try that. So sub x is the fourth root of root 27. Um, into d squared dy. Okay. It's enough to then just substitute it into this equation here and hopefully get 0. Because obviously, like I said, the denominator will not affect whether the fraction is 0. So the only time it's 0 is if the numerator is 0. So therefore, minus 18 of fourth root of 27. Actually, no. Would it simplify? No, actually, so that's minus 18. There we go. Don't know why there's an x to the 4 there. An x there. You might be able to solve it, maybe. Yes, you can. No, you don't even need to do that. Sorry, you could. I think you would be fine by substituting it in, but I think we can solve it actually. I just thought you'd get a nasty polynomial, but actually see that this will go to minus 18x to the 4, and then 81 times minus 18 gets us minus 1458, and then we had 18 times 4, which is going to be 72 x to the 4. And now we've got x to the 4 and then a constant, and that's equal to 0. Where we can group the x to the 4s together. So 72 minus 18 gets us 54 x to the 4. And that's going to equal 1458. Therefore, x to the 4 is going to be 1458 divided by 54. And that's going to get us 27. And there we go. Therefore, x is the 4th root of 27. There we go. Okay, I thought it would be a nasty, but then I realised the only terms of x we're going to have is x to the 4. That I can solve like I just did. There we go. So, but I think you could substitute it in as long as you get the second derivative 0. That's really the same thing. But anyway, we then show the only point of inflection could be the 4th root of 27. Notice I said could and not is. That's because d squared x over dy squared equals 0 is only one condition for a point of inflection. What we also need to consider or check the signs of the second derivative. What gives it d squared x? D squared y. Oh. Around x is 4th root 27. So before x is the 4th root 27 and after, or 4th root 27. So, okay. So the size. Well, first of all, this is a square, so it's always going to be positive. So the sign will only change depending on the numerator, because the denominator will always be positive no matter what, because it's a square number. So I'm going to say denominator of, what was it? What was the denominator again? X to the 4 at 81 is always greater than 0. Greater than 0, because I don't want to equal 0 because it's a denominator. I don't want to divide by 0. Is always positive. So consider numerator, right? And the numerator is going to be again minus 18 x to the 4 at 81, wasn't it? So I'm looking up here, right, this numerator here. Add 18x of 4x cubed. Okay, now I'm not setting it to anything. But what I want to do first is simplify it. So then I can consider, and it'll be more obvious what happens if I take x is less than 4th root of 27 and x is greater than. That will make it easier to simplify it. So that will be equal to minus 18x to the 4. And remember that was minus minus 1458. And that will go to this bit 18x, which was 72x to the 4. And that went to 56x to the 4 minus 1458. Okay, so right. So this was equal to 0 when, remember, x was the fourth root of 27. Okay, cool. So then what about when x is greater than fourth root of 27? Well, again, you could, well, you could say, well, if x is fourth root of 27, then that would mean x to the 4 is 27. So therefore, you want to consider when x to the 4 is so if then x to the 4 is greater than 27, then 56x to the 4 is greater than, if it then times by 56 times 27, that's going to be, wait, was it 52 or 56? It was 54. Okay. 1458 and 52, 54, not 56. Oh my lord, my time's in it off. Well, no, I did time. I forgot. I was trying to remember what I did before, but I messed it up. Okay, so then 54x to the 4 is going to be 54 times 27, right? So that has to be greater than 1458. But therefore, d squared y over dx squared is this bit here is going to be greater than 0, right? Because the 54x to the 4 is greater than 1458. So therefore, that's greater than 0 when, well, x to the 4 is greater than 27. So that is also means when x is greater than the fourth root of 27, right? And likewise, then, if we then said if x to the 4 is less than 27, so if you said x was less than the fourth root, that would mean x to the 4 is less than 27. Then 54x to the 4, likewise, is then going to be less than 1458. Therefore, this then is going to be less than 0. So it'd be negative. So therefore, d squared y over dx squared is going to be less than 0 when x is less than the fourth root of 27. Therefore, there is a sign change. Uh, how am I going to express this? There's a sign change around fourth root of 27, but I want to be a tad bit more precise with how I word it. So there's a sign change on second derivative of d squared y dx squared when x is less than the fourth root of 27 and x is greater than the fourth root of 27. Therefore, because also the second derivative is 0 at x is root 24, therefore x equals fourth root 27 must be a point of inflection. Okay, because that's the two criteria, right? You need to show that the second derivative is equal to 0, which isn't too bad, but then you need to show around, so before and after the point, there is also a sign change in the second derivative as well. Okay. Um, cool. So that's a point of inflection, and hopefully, that the point of inflection doesn't really get covered too much. They don't ask about point of inflection often, but they could ask, and I think this is a really, really nice question that actually ties a lot of differentiation together in this one single question. I think this is a really, really nice question to really practice your differentiation. And again, it's a hard one, and you can ask. Well, they could. I expect a tricky differentiation question to come up. It could look like this. So this is a good question to practice. But yeah, hopefully it made sense. Okay. Uh, Okay, so I'm on the last question now, and it's a proof of contradiction. And again, will probably come up around on paper two, because there was a contradiction in paper one. And there are various different proofs. For example, you do need to know like root 2 or root of anything is irrational. And you also need to prove there are infinitely many primes. Those are the two main ones you need to learn. But there's some other ones you can practice. And these are, and I guess this can be one of them. But the mechanism will always be the same. But let's have a look. So it's saying proof by contradiction, there are no positive integers p and q such that this is equal to 25. So first of all, I need my assumption, and our assumption is going to be the opposite to what we want. Ugh. So my assumption is, right, saying there are no positive integers p and q such that this happens. So actually then I'm going to say there does exist positive integers p, q, such that 4p squared minus q squared is 25. So this equation does hold, okay? That's what I'm saying. For some positive integers p and q. Okay, so that's the opposite, right? So you assume the opposite. So there are no integers. Well, then the opposite is there is a solution. So there is a positive integer solution. Anyway, so then we need to do some stuff. Well, the first thing I spot is this is the difference of two squares. So I can factorize and say 2p minus q and 2p add q is 25. Okay, so actually I have two factors here. I also notice, again, that p and q are integers. So this means these are going to be integers. So these are going to be the integer factors of 25, right? So actually, I can then consider all the integer factors of 25. That's going to be 25 and 1, and then 5 and 5, right? Those are the only factors. Uh, Again, you could do prime factor decomposition, right? So 25 is 5 squared. But those are the factors anyway. Okay, but also they could have plus or minus. It could be -1 or negative 25, -5. Because, for example, -5 times -5 still gets us 25. Okay. So we need to consider this. So there are really, initially there are 6 cases, right? So it's going to be, uh, we have the factors 25 and 1, 5 and 5. I know 3 cases, but there's 6 factors. Or then it's going to be -25 and -1. Because then now we're time to give positive 25. And then -5 and -5. Okay. Because obviously, because the reason I can't immediately rule out, because whilst they're both positive, 2p minus q, p could be 1, and then q could be like 2. No, q could be like 3, because then 2 minus 3 you get -1, for example. So that could give us a negative number. Uh, but 2p plus q is always going to be greater than 0, because we're adding two positive integers. So that's telling us at least one factor must be positive. So therefore, these can't happen because both factors would be negative to then give a negative times a negative to get positive 25. So we rule those two out immediately. So therefore, -25, oh, -1, -5 cannot be factors of 25 here. Okay. And actually, this is something you need to consider. But in the mark scheme, they don't get a mark for considering it. You can't just jump to this case immediately. But you have to be a bit rigorous, right? Well, not rigorous, but you do have to consider like things that can happen. But yeah, so then we just get these two. So therefore we have two possibilities. So case one, that's going to be factors 25 and 1. So therefore that would mean 2p minus q could equal 25, and then the other factor 2p plus q would be 1. Then we could solve it. Now you could just put it into a calculator, but I could then say, well, then I can immediately spot I can add them to get rid of the q because it's q minus q. So that would mean I could then get 4p would equal 26. Then p would be 26 over 4, which is not an integer. It's 6.5. So this has no integer solutions, okay? For p, okay? There we go. So therefore, and because p is an integer, that can't happen. Or we could reverse it and say 2p minus q would be 1, and then 2p add q would be 25. Okay, so I'm reversing it, right? Because I could say either or. So I could switch the factors around essentially, because obviously multiplication AB is equal to BA. Okay. But anyway, then we solve it. So therefore, then you could say, well, again, 4p would equal 26. And p would again be 6.5. So this also has no integer solutions for p. Cool. But p is, I'm going to say integral, which means it's an integer via our assumption. So case one cannot happen, okay? So the factors cannot be 25 or 1, okay? So actually I'm going to just then say, well, case one cannot happen. So that means 1 and 25 cannot be factors, okay? Cool. But then we have the other case where instead, if we go back up here, if it lets me, we have 5 and 5, okay? So we did 25 and 1. Now we need to consider if they're 5 and 5. So that means 5 and 5 are factors of 25 instead of 25 and 1. Therefore, the factors are 2q minus, no, was it 2p, wasn't it? Minus q is 5, and 2p add q is 5. Yes. Cool. And actually, we don't need to reverse it like we did in the case one, because if we flipped 5 and 5 around, it's still 5 either way. So it doesn't matter which way order, they're both 5. So they don't need to, you know what I mean, flip it around like we did before. Okay, so then therefore, again, 4p is going to be 10. Then p is going to be 2.5, because then we're adding both equations to solve it. So then 4p, and then q minus q goes away, and then you get 10, and 5 and 5 is 10. But then p is 2.5, so this also has no integer. Solutions for p, okay? So actually, we've ruled out that there are no factors that give, what have we said here? Well, 2p minus q and 2p add q, they cannot be factors of 25, but they have to be because we factorize it as two factors and they have to be integer. So we've gone wrong somewhere. But the only thing we did was make an assumption. So if we made one single assumption and then every other bit of maths we did was correct. Well, the maths isn't incorrect. The only thing we changed was the assumption. So if the assumption was changed and then the maths was correct, but then we got somewhere wrong, that means the assumption has to be wrong. Okay, so therefore, how would we say this is so therefore I then use this symbol. This symbol you can use, it means a contradiction, right? And a cross with 4 dots on either side. So that's a contradiction because uh, uh, 2p minus q. How do I want to phrase this? Therefore, okay. Well, 2p minus q and 2p add q cannot be 1, 5, or 25, right? Um, so, oh, so cannot be integer factors of 25. But we said that 25 again was 2p minus q, 2p add q. So 2p minus q and 2p plus q must be an integer, must be integer. Oh, it's getting slow now. Must be integer factors of 25, right? Because it's a factorization. We express 25 as 2 different factors. So these must be integer factors. So we have a contradiction. So therefore, contradiction, which means our assumption must be false. Because, like I said, the reason why the contradiction works, the mechanism, you assume something different is true that you're not sure about. So you assume that's the opposite is true, but then you do the maths with that assumption, and then if you then you do the maths and the maths is right, but then you lead to something wrong. Well, if the whole maths is right up from here, all the maths we did down here is right. But then the only thing we not really did right was the assumption. So therefore, the only thing wrong in this whole thing must be the assumption. If the maths that followed was right, but we still broke down somewhere. So that tells us this must be false. Therefore, the opposite must be true. Okay. Um, because remember, we assumed the opposite of the statement was true initially for the assumption. So the opposite is false, and the other opposite is true. So therefore, the statement originally that no positive integers, p and q, then that must be true. So therefore, there are no positive integers p and q such that 4p squared minus q squared is 25. Right, that's the original statement. If you then just copy it up here, remember it said there were no positive integers p and q such that 4p squared minus q squared is 25, and we got there. There we go. Yeah, this was the final question, by the way, so it's not the easiest. But yeah, hopefully you've seen it now. Hopefully it made sense. I did go in a lot more detail than actually the marks can expect you to do. It is only 4 marks, but hopefully I broke it down clearly. And you go from there. But you really only get marks A for making the assumption statement. Then you get marks for just solving these simultaneous equations and then getting P's a decimal. And then at the end, obviously, you conclude there's a contradiction because you got no integer solutions. So the assumption's false. But I did went in more detail with my explanations and stuff like that. But, you know, that's the whole essence of this question. Okay, I'm gonna leave that there then because it's getting late now. But obviously, I do apologize for earlier. But obviously on YouTube, I'll try and cut that out. Um, when I had to go away for question 9 for a bit. Um, at the start. Well, yeah. Um, that's this part done. I did do part 1 as well. So remember part 1. If I leave it. Remember, I did questions 1 to 8, which I do very, very much recommend you go over as well for your paper 2. Oh, it's slowing down now. Yeah, I think my laptop's telling me to stop now. So remember, it was these questions which will be in part 1. I'll link part 1 actually as well, but also I will be combining them as a whole video as well. Where you see the whole all 14 questions, right? Um, but these, remember, this is what we did in part 1, so I recommend you look at that. But yeah. I'm gonna leave that there then. I'm gonna do one more. I should do one more revision session on the night before. Go over some other questions likely come up. But yeah, so that's it for now. So hopefully this will be of use to you. But I'm gonna leave that there then.